Welcome everyone to Pure Virtual C++ 2022. This is the third year we have ran this conference. Started off wanted to make a conference for C++, which is all free, all online, which you can watch the content of after and that anyone can come along to. So what we have today is 5 sessions on a broad variety of topics. They're going to be streamed on a bunch of different places. They're on Learn TV, they're on Twitch, we're on YouTube. But if you do want to ask questions to the speakers, I would recommend you hop over to Learn TV, where there's a live chat. Folks will be watching that. Speakers can pick up questions from there and answer them. Note, if you do pop along to Learn TV and want to ask questions, all of that chat is under the Learn TV Code of Conduct. So please do be aware of that. My name is Cy Brand, and I'm going to be your host for today. We're going to be running about 3 hours for the entire conference, just straight through to the end. So there won't be many breaks. Feel free to hop in, hop out, check out what content you want. But please do chat to the speakers. Let us know your thoughts. Now, the first session is going to be presented by myself. I'm going to be talking about what's new in C++ 23. So we can get started on that right away. So if you want to go and look at what is new in C++ 23, you might head over to something like CPP reference and be hit by a page like this, maybe, which is great if you want to see absolutely everything which is available, look at all the papers, see all the documentation, but this is a lot to digest, and there's all of these defect reports. It's maybe not immediately clear to you what is useful for you to apply in your everyday coding, what makes C++ better. So the aim of my talk today is we don't have a whole lot of time, about 30 minutes, so I'm just going to pick a bunch of these which I think are interesting and try to show them in a fun way using my cats. I have 3 cats. One of them is sitting actually right next to me right now, sleeping. I'm sure he will probably join in the conference at some point. We have Marshmallow, Lexical Analysis Cat, and Milkshake. As you may guess, I named the middle one, and the other 2 were named by my kid. They will probably join the conference at some point, but I'm going to show a bunch of small programs, all involving my cats, which can teach you something about C++ 23. So let's get started. Treats. Now, I don't know about your cats, but my cats all like treats. And they're also a little bit jealous. So if I give one of them a toy or one of them a bit of chicken, then the others are going to want one too. Now, this can be a bit of a problem. Basically, I need to have enough toys, chicken, and catnip for each of my cats. So how am I going to code this? Well, I could take my range of treats, my toy, my cat, my chicken, and my catnip, and I could extend this out like this. So I can have maybe a box full of toys, a box full of chicken, and a box full of catnip. Now, how do I do this transformation, this single range of 3 items into a nested range where each item is triplicated? Well, there's a few different ways I could do this, but let's have a look at using C++ ranges. So let's start with our single dimensional range and then try to turn it into this. It's still single dimensional, but we have taken each element and multiplied it by 3. So one way we could do this is taking our treats and piping it into some custom range adapter. There isn't a range adapter to do exactly this in the standard library, but we could write one of our own and maybe call it my views repeat range n. So we'd give it 3 to say, take every element and multiply it by 3. So we're still in our single dimensional range. Then we want to chunk up our range into multiple dimensions. And one way we could do that is then taking this result and piping that into std_views chunk and giving it this size 3 of the chunk. So this is our first new feature in C++ 23 that we're talking about, std_views chunk. And the thing which you see which has a star next to it in this presentation is a new C++ 23 feature. There's also a cousin feature. A bunch of these come in like pairs or threes. This comes in pair. We've got chunk and chunk by. Chunk takes a size for the chunks. Chunk by takes some predicate, which is run over your range in order to generate those chunks. But now maybe we want to reuse this. Maybe we have a bunch of places that we want to expand out our range and then chunk it. So maybe we want to give it a name. We'll call it repeat groups. So if we say, take something and pipe it into repeat groups of size n, it's going to expand the range by that size and then chunk it by that range, by that size. How could we do this? Well, we could create our own range adapter. We could do this completely by hand, or we could just compose existing ones. So like we just showed, we could use our repeat range n and our chunk. So here our repeat groups is just a closure object, which calls repeat range n and then chunk. Note, there's no range here. We're not piping a range into these things. We're just composing them so that they can be used later. We're creating our own range adapter object out of existing ones. Now, I don't quite have time to show you how to write this in the implementation of repeat range n because it's quite complex. Note that this is a new feature in C++ 23, being able to compose our custom ranges with the standard library ones. If you do want to see an example, you can go check out that Godbolt link. Then maybe we take this and we look at the assembly output and we realize for some reason this is not getting inlined. I don't know. We could put an attribute on the lambda. In C++ 23, you can now do this, put an attribute on a lambda. Maybe a contrived example, but this is just to show you this is now something which you can do. This is especially useful if you have additional tooling which looks at attributes on functions and does a static analysis or some additional work. You can now decorate your lambdas with these. Okay, so let's take a little bit of a step back. We've thought about how we're going to split up these treats, but then maybe we do a bunch of work with our cats. They're not so jealous anymore. We can just, give one of them a toy, one of them chicken, one of them catnip. Well, one thing we could do is just allocate each of these to a cat. So we can take our vector of treats and we can take our vector of cats, just marshmallow, milkshake, and lexical cat. And then we just want to match these up. We want to zip them. So we can use the new range adapter in C++ 23, zip. This just takes our cat range, our treats range, and matches up each element, and will give you back a pair like this. So we would get a pair of marshmallow and toy, pair of milkshake, cat, chicken, lexical cat, catnip. Of course, you don't have to just have two ranges here. You could pass 3 or 4 or 5 ranges, in which case it wouldn't give you a pair, it would give you a tuple of the size of the number of ranges you pass. There's also a cousin of this called zip transform, which instead of giving you back a pair or a tuple, you will give it a function and it will call that function with that pair or tuple as the arguments. And then each element of the range will be the result of calling that function with those arguments. And this will be done lazily, just like with std transform. So it's not going to zip everything together and call all the functions and collect it up into a range. You just give it cats and treats and a function. And every time you ask it for a new value, it's going to call the given function on the next pair and give you the result. So this is done lazily. But maybe we do want to put this into some data structure, like a map. So we want to take our lookup table and say, hey, what treat is allocated to marshmallow, or what treat is allocated to milkshake? Well, we want to essentially convert it into an unordered map or some other kind of hashing data structure, maybe. We could do this in C++ 23 using std ranges 2. Std ranges 2 says, take this range, which is potentially lazily generated, and stick it into a container, convert it into some container. So you could give this an unordered map, you could give this std vector, and it would give you a vector of pairs. A bunch of different things you could do here. Note that I'm not actually having to specify the key and value type of the unordered map. This will be deduced for me. This is quite handy, especially if there's a lot of machinery on top of this. Maybe you can't easily tell what the key and value types are, where you can just say unordered map, work it out. Okay, so we've now given our cats some treats. We've done some work, we've done some training with them so they weren't jealous. Maybe we want to do some more training with our cats. Maybe we want to, instead of just giving them food, we could offer them food and they have to give us their paw, and we shake their paw, and then they open their mouth and we give them a treat, and then maybe they make a mess, because my cats make a ton of mess when they're eating. How could we express this in code? Well, one way we could do this is something like this. We have our cat type down at the bottom, which has an offer food function. And this returns an optional paw. So maybe the cat, we gave the cat the food and the cat put out its paw. Or maybe the cat forgot that it was supposed to put out its paw, or got bored, or saw a mouse, or I don't know. There might be any number of reasons why it might not give us a paw. And then we shake the paw, and then maybe the cat wanders off because it saw something else out. All of these are returning an optional because they might not happen. The cat might not make a mess. It's kind of unlikely, but it might happen this time. So how do we then code up this function of feeding the cat, offering the food, and then if it offered us the paw, then shaking, and then if it offered us a mouth, so on? Well, we could just do it like this. We could say, offer the food, and then we maybe get a paw back. So we check if we did get a paw, and if we didn't, then we return null opt. And then we shake it, and maybe we got a mouth, so we check it, and if not, we return null opt. And you can see that the more and more steps we add to this, the more noisy it gets, the more code we have to write to just marshal this data around. Really, we just care about doing these steps. Like maybe we could format it like this. We could use the if initializers to do this work. Maybe you prefer this. We just do the offer food and check it in the same line. But again, the more of these things you add, the more it's going to shift horizontally. It's not going to be very pleasant. There's just a lot of noise here. We just want to say offer the food and then shake and then feed, and that's it. Well, in C++23, you can do pretty much exactly that. You can say offer food and then shake and then feed. This reads pretty naturally. Even if you maybe don't know C++, you can kind of work out what this is doing. So this is part of the new monadic interface for std optional in C++23, which is actually a paper that I wrote. So I like this feature. This comes with a few things. There's and then, which allows you to compose functions which return optionals, just essentially crushing them together. And if at any point something returns null opt, then the whole thing is just going to return null opt, and the rest isn't going to happen. Then there's std optional transform, which allows you to change the value stored inside the optional as long as there is one. If there isn't, then it's just going to be null opt. And then finally, there's std optional or else, which lets you call a function if the optional was empty. So these are some helpers just to make dealing with optional a much nicer, cleaner, more ergonomic experience. But maybe we look at our code, we decide we don't have much information here, right? We said that a bunch of these things could fail for a variety of reasons, but we don't have that information in our code. We just get null opt. Oh, the cat didn't give us a paw. Why not? Null opt. Didn't make a mess. Why not? Null opt. So maybe we would like some information on why something failed. Well, C++ has something for this. It's called std expected. You might be familiar with this as like Rust, as the result type in Rust, or in a bunch of other languages have something very, very similar to this idea, or the either monad. It's the same kind of idea. Either we have the expected value, the mess, the mouth, the paw, or we have something representing the unexpected case, the error. So in this case, our error type is that representation of the error. It's going to give us some information about why this thing failed. We don't yet have the same monadic interface the optional is getting in C++23. There is a paper in flight. I don't know if it's going to make C++23, but hopefully at some point, std will have the same kind of interface that that std optional now has in C++23. But how would we implement expected? Say that we're implementing the standard library, or we're wanting to make some changes to std expected. We decide to write our own type. Well, let's look at maybe one function is the value. You want to get the value type out of this thing. But you also want to maintain the const ref qualifier of the wrapping expected object. You can maybe hear the washing machine in the other room just started. Unfortunate. So we have to write this 4 times. We have to write the const ref qualified version, the ref qualified version, const ref ref, ref ref. This is a lot of noise, kind of like my washing machine. This is my washing machine. You don't want to write this code for every single member function you have in your type, right? You're going to quadruplicate everything. It's easy to get wrong. It's hard to maintain. It's just not what you want to be doing. So C++23 gives you something for this. It's called deducing this. So this says, I don't have to overload these things anymore. I'm just going to deduce the const ref qualifiers of the explicit object parameter. This used to be the implicit object parameter that we don't see in the declaration. Now we see it in the declaration. This function takes a single parameter called self and is qualified with this keyword, which says this is special. This represents the object which you called this function on. So now if I call value on an R value, then it's going to be deduced. Self is going to be deduced to an R value. If I call it on an L value, it will be deduced to an L value. So this gets rid of our quadruplication of code. It also solves some other things. This lets us do recursive lambdas, funnily enough, because we suddenly have access to self inside the function. It also lets us do CRTP, the curiously recurring template pattern, without having to template our type on the derived type, because self here can be a derived type. It doesn't necessarily have to be expected. Like if you derive something from expected, it could be deduced to that. So we would no longer, our CRTP would be a lot simpler. It also fixes a few other nooks and crannies of the language. I worked on this paper as well. I would recommend giving it a look, because there's a lot of things which kind of fall out of this design, which are not immediately obvious. This is maybe my favorite C++23 feature. I think this will clear up a lot of code, especially library code, if you have to write this kind of thing. Okay, so now our cats are pretty well trained. They've done a really good job. We want to give them a bunch of treats. So maybe we just want a treat generator, something which just generates us as many treats as we want, and we can just give them to the cats. Okay, so we have std generator. We have our treat generator, which we get from something we're calling make treat generator, which we'll see in a bit. And then anytime we want some treats, we just say, okay, well, this is an infinite range. This is an infinite range of treats. We're just going to take 10. You could use any kind of range adapter you like here. It's just a range. This is an infinite range of treats. We don't care where they come from. They're just there somehow. Std generator isn't yet voted into C++23. My understanding is it will be, but it's not there yet. But even if it doesn't make 23, there's a bunch of open source implementations, including one which I wrote, which you could use instead. So let's have a look at how this works, because this is an infinite range. where are we getting these treats from? Well, one implementation of make treat generator could be we start off with some number of treats, say 50, and then we have an infinite loop. If the number of treats we have is 0, then we're going to go get some from the shop. And then regardless of whether we did that or not, we're going to decrement the number of treats and yield back a new treat to our caller. So this co-yield treat keyword, because our return type is a std generator, what this co-yield means is halt execution of this function, of this coroutine, because this is a coroutine, give the caller back this treat, and then later I can be resumed and we can go around this loop. So even though this looks like an infinite loop, which is never going to stop, our function isn't just going to loop forever and our program will never terminate. This function is going to suspend on the co-yield, and then when we ask it for another value, then it's going to go around the loop. So this will be the first standard library coroutine we would have. There are a bunch of different kinds of coroutines we could write, like tasks, shared tasks, whatever, but this will likely be the first one that we get. Okay, but how do we get our cat object in the first place? Well, unfortunately, the API which I deal with for getting my cats is a very old crufty C API. It looks something like this. We have a getCat function which takes a pointer to a cat, and it will allocate a cat somewhere and then fill in this pointer, and it's an out parameter pointer essentially. And you give it the color of the cat that you want, which is represented as an int, even though we have an enum for it in our nice C++ code. And then we have a deleter function because we want to reclaim the memory for the cat once we're done with it. So how are we going to use this in our nice C++ 23 application? We don't want to forget to reclaim the memory. We don't want to be dealing with the int for the color when we've got nice enums, things like that. So we want to be using like a unique pointer for this, right? So maybe we'll create a type, which will be our cat deleter. And then we'll do something like this. We'll create a unique pointer with our cat deleter. But then in order to get our cat, we need to create a cat pointer, give it the address of that. We need to static cast our color to an int, and then we're going to reset the unique pointer to the raw pointer. You could potentially just construct the unique pointer instead of doing a reset, but maybe this unique pointer is a member function, and you can do this in the member initializer of the constructor. You'd have to call reset, and this gets even uglier if this wasn't just an out parameter, if this was an in-out parameter, and the C function had to look at the current state of the unique pointer in order to give you back the return value. You basically have to do this resetting. You have to manage the memory of the unique pointer, maybe release it. It's just kind of a mess. The static cast int, we need to be thinking about what type we're casting to. In this case, we look at the declaration for getCat and we see it as an int, but maybe we don't know what the underlying type of the enum is. There's a few things going on here. Static cast are just kind of nasty. So C++ 23 gives us some tools to help with both of these things. We now have std out pointer, which handles that resetting and everything for you. There's also in out pointer, which is for that use case where it depends on the old value of the unique pointer. Then we have std to underlying, which will take the enumerator and cast it to the integral value of the underlying type. We don't have to do static cast. We don't have to think about what type it is. We just say, give us the integral representation of this thing. So this, I think, is a much more ergonomic solution. A few things here which have cousins. Out pointer, I already mentioned. In out pointer, for determining if something's a scoped enum, we now have a type trait for that. And since we're using unique pointer here, can quickly mention that you can now use Constexpr unique pointers, which is very cool. On that note of unique pointers are, of course, move only. You cannot copy them. And this has a few knock-on effects for usability. Like, for instance, if we have a cat action, which is some action our cats might take, which gives us back some mess and it has a name associated with it. What if our action here has to capture a unique pointer? Like this. Say we have a cat pointer, we have a cat action, and we have a lambda which captures this unique pointer. This does not compile because std function does not support move-only closures, and this closure is move-only by virtue of having a unique pointer as a member. So this isn't great. One way we can get around that in C++23 is using std move-only function. So this is very similar to std function. There's a few differences which you can look up, but the basic idea is that you can use this for move-only closures. Okay, so we've dealt with all our unique pointers and our CrufTC interface. Now we want to make something a bit nicer to use. Maybe we want to get a cat from a color. You know, I have 3 cats, as I mentioned. I have a black cat, a tortie, a ginger cat. I don't have a calico cat or whatever other colors that you might put in this if it wasn't on a slide. But we want to give a nice interface for giving a color and getting back the correct cat. So one way we could implement this is we can use the using enum feature, which was C++17 or 20, I can't remember, a relatively recent feature, to say, okay, if it's black, return lexical cat. If it's ginger, return marshmallow. If it's a tortie, return milkshake. And otherwise, use std unreachable. Std unreachable is if you're used to like built-in unreachable, which is a compiler intrinsic in a few compilers. It's the same thing but standardized. Basically says, hey, this is undefined behavior, and the optimizer can assume that this didn't happen, which in some cases can give you some nice performance improvements. Okay, so we've got a nicer cat from color implementation here. What other things do I do with my cats? Well, my cats like to sit in boxes. Right now, Marshmallow is here. He's not in a box. He is on top of the cat bed, which I bought him instead of inside it. But my cats like to sit in boxes, and I like to keep track of where the cats are. And so I have a big array of boxes. I then have a multi-dimensional span over my boxes. I don't think MD span is making C++23, but this is also something which is in the works and you can find open source implementations for. So I've got a bunch of boxes which might contain cats, and I have a multi-dimensional view over this single dimensional array. How do I index this thing? Well, in the past, maybe you used like a call operator, or you use 3 sets of square brackets. But in C++23, we can just have a single set of square brackets and just put commas inside them. We have a multi-dimensional indexing operator. This is nice. This is one of those like really small things which actually makes a quite nice usability improvement, I think. And maybe for whatever reason, if we wanted to make sure that we were saying these are size t's, we could use the new std size t, the new std size t literal. And I'm just seeing in my StreamYard chat that Daisy's saying the MD span is still on track to make 23. So that's good news. Hey, there should be a star here for this being a C++23 feature. So that's great. Yeah, if you wanted to say that this was a size t, then you could use these new literals. Maybe it doesn't make sense in this case, but in other cases it might. So now that I've had all of these boxes, I want to track who's in boxes and which boxes they're in. So I have a little monitoring chip, which has some machine learning stuff, and then has a little display, and I can communicate with remotely. It's wonderful. And so a couple of functions in it are, of course, I have to collect this box data, which cats are in which box. I need to pack it into some format I can send over the network, and then I have to actually do that job of sending it. So in my dispatch box data function, something I could do is pack up my box data and then send it over the network. But I know that my specialized chip has a different byte order than the network, so I use this new std byte swap to just flip the bytes into the correct order. This might compile down to a single instruction on your processor. So maybe if you used to use intrinsics for this, you can now use the standardized version. Now, how do we pack our box data? Well, my chip has specialized hardware for doing this because I designed it myself, but I can't call it at compile time. I have a compiler intrinsic, but it's not Constexpr. So how do I deal with this? I still want to do the most efficient thing at runtime, but I might also want to do this thing at compile time if I have some box data that I know ahead of time that I want to send somewhere. So one way I could do that is using the new if const eval. So if const eval says if I'm being compiled at if I'm being run at compile time, we're going to do this thing. Otherwise, we're going to do this other thing. So at the top here, I have some more costly Constexpr friendly algorithm, and in my else branch, I have my compiler intrinsic. And maybe my implementation of if const eval might have it might use these new CMath functions, which are now said to be Constexpr friendly. Okay, but what if something goes wrong? Maybe something goes wrong and I want to display an error. I want to maybe display the stack trace or something on a little hardware display that I have next to my desk. So one way I could do this is my hardware has this function I can call to just get a display buffer. This is just a bit of memory mapped. It's some memory mapped I/O which I can just write into, and it will just appear on the little screen I have next to my desk. So one way I could use this, if result was false, then I'm going to get my display buffer and I'm going to make an O span stream of it. This is new in C++ 23. It's kind of like string stream, but it's for when you have already allocated backing storage that you'd like to use instead of dynamically allocating under the hood. Then if I want to write out the stack trace, I could use my new C++ 23 std stack trace. There's quite a fair bit of API surface area here, so you can go look at the documentation for this. But basically, this gives you the ability to get the current stack trace, to iterate through the frames, to print them out, things like that. Quite handy. My little chip also has some commands which you can issue over the network, and these need to be semicolon separated. So if I have a bunch of commands which I've already written, then I could semicolon separate them using the new std views join with function to just take this range and join them all into a single thing with this delimiter. And then maybe I dispatch this over the network and I get back a string response. Something might have gone wrong. I know that something gone wrong if at any point in this string there is the word error. And what I can do now in C++ 23 is I can check if a string contains another string without having to do .find is not equal to string npos. So this is just one of those tiny things, but I'm sure you've had a bunch of times you're like, does this string contain something? How do I do this in C++? Oh, I use this nonsense. Now you can just say .contains. It makes much more sense. And finally, when my cats are about to go to bed, I like to get them to count sheep so that they sleep well. So I have a function which helps them count sheep. One way I could do this is I could create a vector of just 100 zeros. I could then make this vector count from 1 to 101 by using the new stdranges iota algorithm, which will just fill in 1 up to 100 in this vector. And then if I want them to get them to count this, I can just loop. While this isn't empty, we're going to shift the numbers to count left by 1 and get whatever we shifted off the end and count that. So stdranges shift left just takes the range and shifts it left the number of elements you tell it to. And then, as you might expect, there is also shift right. So that is now my cat to bed. This presentation is also getting to bed, so this is a outline of everything I talked about. I'm not going to read off this slide. That would be horrifically boring. But if you want to take a screenshot or anything, this is all of the features in C++ 23 which I mentioned in this talk. There are a few things which I didn't mention. Some which I think are interesting are ranges starts with and ends with for finding prefixes and suffixes. StdView slide, which gives you a sliding window view over a range. Adjacent and adjacent transform, which are the same, but the instead of a runtime size window, it's a compile time size window. Then there's std invoke r, which is like std invoke, but you can also give it a return type to convert the return to. And then there's a couple of type traits for working out if you're going to have a potentially dangling reference. There's a few other things which I didn't have time to cover and didn't want to put on this slide, so you can go back to that CPP reference thing if you really like, or Wikipedia or whatever your preferred source is. But I think these are most of the ones which are interesting to most users, I think. So thank you very much, and I hope that you enjoy using C++ 23. I'm going to check for questions. I think we're pretty much on time. So if anyone has any questions, you can head over to Learn TV and stick them in there. And as soon as we dry up on those, then we're going to move on to the next session. Yes, and now, of course, those topics are in this talk because I wrote them in. Yes, it's a comment saying now these topics are in the talk. So yeah, I guess so. I've got a question here. Are we settling for and then and not then in C++? Yeah, so this is an annoying naming thing. So you might have seen like std future got .then, but my recollection of .then for std future is it's not quite the same as and then. And then is essentially like just a monadic bind. I think .then for futures is somewhere between monadic bind and functor map, but I might be wrong on that point. But yeah, this was a whole thing. I'm sure you can imagine the bike shedding which goes on with this kind of thing. I'm getting confirmation from Daisy that yes, future.then is like between monadic bind and functor map. So yeah, that's why it's not the same name, because it's not quite the same thing. Okay, I'm not seeing any other questions, so I think that is a great time to move on to our next talk. So I'd like you to all welcome Daisy Holman, who is going to tell us about some cute code which we should learn from and never write. Hey Daisy, how are you doing? Oh, you're muted right now. Of course, it wouldn't be a virtual conference without having someone muted when they're not supposed to.
Oh, we did a tech check, and then I muted to just be safe, just in case. Though I was backstage and stuff. But yeah, nice talk. Thank you so much. There was some very interesting things there.
Yeah, thanks. I basically I wrote a big Twitter thread in order to teach myself all of the different features, and then just stuck them into talk involving cats. So. All right, I'm gonna hand you all over to Daisy. Take it away.
All right. Are my slides showing up on the screen? I don't see my slides yet. Oh, there they are. Wait, nope. Those are size slides. There we go. All right. So yeah, I'm giving another cute C++ tricks talk. Some of you may have seen my talk back in at CPPCon last year, where I gave kind of part 1 of this talk. This is part 2 of this talk. if you're not really familiar with what I'm going for here, basically we're just going to hang out for 30 minutes and have some fun with some weirdnesses of C++, but there is a point to this, and it's really that we want to learn some new things about how C++ works, and it's quite easy to kind of remember these things when we use them in these bizarre ways, right? These things that the kernel of truth in these tricks will come up in real code, but hopefully the way that we're using them here won't actually come up because it's just so bizarre. But hopefully we will get some ideas of how to do the same thing the right way, if it is in fact a thing that you should be doing. And most importantly of all, I think we're gonna try and talk a little bit about like how do you learn these things, right? How do you play with the language in ways that will enable you to learn new things about the language and have them stick in your mind. As always with this kind of talk, disclaimers: don't use these tricks directly in real code. Don't copy them like you would from Stack Overflow. Don't copy code from Stack Overflow either. That's also a thing. But do use them to learn things that will help you understand existing code. And this is just to basically say the same thing as the first bullet. This is not a software engineering talk. This talk is about surprising snippets of code, and well-written code should be unsurprising. And the definition of unsurprising can definitely depend on your audience. I've presented some of these before and had people say, oh yeah, I use that one all the time. And that's because they're writing for an audience where that code is unsurprising, right? Somebody who writes a compiler or has been working on C++ for years will understand the implications of some of these things maybe better than your general audience. So always, always, always write code that should be unsurprising for your audience. Think about your audience when you write code. I do have a problem in most of my talks of getting too into the weeds. So I've just kind of leaned into it in my last few talks. This talk is all weeds. It's going to get very into the details of what's going on in these snippets and what's interesting about some minutia of C++. It's actually several mini talks. I'm going to kind of jump around depending on how time is going and go through these tricks, trying to leave enough time for questions. So I may skip some of them. I have 3 tricks prepared. I don't think I'll get to all 3. I'm just going to try and fit them in based on time. So anyway, let's jump in and we'll have questions at the end. So here's the first trick. This is, I tweeted about how you can use assert in Constexpr rather than static assert. I think most people who have tried to use static assert in a Constexpr function have kind of looked at it sideways and been like, why isn't this working? This is evaluated at compile time. And so we're going to talk about why that doesn't work the way you think it does. So here's basically the core of the trick. We have this cheesy function that is very simplified A to I, only for unsigned values, that goes through a string and accumulates the value into something to return. We can skip digit separators. The single quote in C++ is a digit separator. So if you didn't know that, that's a thing you could learn from this. And here we need to validate our input somehow. And why not just use assert, right? I mean, the whole goal of Constexpr code looking like it does is that we want it to look like normal code, right? The whole goal behind Constexpr is to have compile time code look like runtime code as much as possible. You might think, oh, if this is only being called at compile time, I should be able to use static assert. And that's actually not the case, and we're going to see why in a second here. So let's step back and say, what does Constexpr mean in C++? This is the committee, and in general the language has a major problem with reusing keywords to mean something different. And Constexpr, static is the most famous case of this. Constexpr is no different, right? Constexpr is at least 3 different keywords, maybe more, depending on how you count. And they all mean very different things that are only tangentially related. And I think, look, in the committee's defense, there is a lot of legacy C++ out there. Every time we introduce a new keyword, we break someone's code because somebody could have used that in their code 20 years ago, and they don't have access to the source code anymore, or they are, have changed things and they have to change too much. So in our defense, we try not to use too many different tokens for things. But I think in this case, we have so many different uses of the keyword that are so distinct that maybe we should have chosen multiple different keywords for it. And I think hopefully I'll convince you of that in the next few slides. But hopefully you'll understand what I mean, at least by that. So yeah, Constexpr depends on which Constexpr you mean. So we have Constexpr variables is one version of that. Constexpr functions is another, where we have Constexpr in front of the function declarator. And we have, as of C++ 17, Constexpr if statements, which we really should have called if Constexpr statements, because if Constexpr statements are, that's the syntax. But we're great at naming, so anyway, if Constexpr statements allow you to do things that in one branch that say some things that wouldn't be legal if the condition wasn't true, right? So and I'm not going to get into the details of that because this isn't about if Constexpr statements, but there's also more. If I have time, I'll come back to this and talk a little bit more. But we're going to focus in on Constexpr functions here. Let's talk about the differences and why I think these are kind of sort of different keywords. So one way to look at the differences here is to look at how what part of the expression or statement does the keyword require to be a constant expression. I'm not going to get into the difference between a constant expression and a core constant expression and an integer constant expression, partially because I don't understand it myself. You'd have to talk to someone who sits in core on the C++ committee, but partially because it's not really important here. I'm just going to loosely use the term constant expression to mean something that can be evaluated at compile time by the compiler. And I'm not going to go any further into technical details of that. But if Constexpr is the other use case, that's pretty straightforward, right? It requires this conditional to be a constant expression, right? But what about Constexpr functions? It's really not clear, right, what they require. Constexpr functions and function templates, you would initially think from these other two that maybe the function body is the part that's required to be a constant expression. And it's not that simple. So let's explore that a little bit more here. So we have, for a function, let's look at how we can use a function that is declared Constexpr. And you're going to see that it's pretty closely related to the other uses of Constexpr, which is probably why it was attractive for us to reuse the keyword, right? We can use a Constexpr function to initialize a variable. So right here you see we're using the function in another place that the keyword is requiring a constant expression, right? Another example is static assert, right? The part inside the parentheses of static assert has to be a constant expression, and we are using our Constexpr function as part of that, right? We can even use it as a non-type template argument, right? This is going to be, you're going to see this less often, but this is a thing that definitely happens and is allowed, right? This is required to be a constant expression, because otherwise how would C++ even form the type? How would it find the definition? How would it find specializations, right? And so that's another place we can use it. But only as long as its arguments are also constant expressions, right? This doesn't make any sense at all. We can't static assert that something we read in from the command line is 42, right? The compiler has no idea what you're going to read in from the command line. So what we did with Constexpr functions to avoid having to write things twice is that we do allow you to use a Constexpr function with runtime parameters as long as it's not in a spot where it's required to be a constant expression, right? And so in this case, since this is just a normal variable, right, and not a Constexpr variable, this just works fine, right? And you're probably used to this, right, in C++. Whether or not you're aware of it, a lot of the standard library is Constexpr, and you use it in runtime code all the time. So what do I mean by Constexpr means maybe this might be evaluated in a constant expression, right? That's what I put in the original tweet. And I think is really the kernel of learning that I'm trying to get to in this example, right? And so according to the standard, a Constexpr function that can never be used in a constant expression is ill-formed, right? Anytime we would try to use increment foo in a constant expression, like a static assert, like the right-hand side of a Constexpr variable initializer, the function is the program is ill-formed, right? We cannot. This function never produces a constant expression, and compilers will diagnose this sometimes. I'm getting to that, but if you put this into Clang, you'll get a error that a Constexpr function never produces a constant expression. But then you have this thing in square brackets that tells you something else weird is going on. -w invalid Constexpr, which is W is not usually used for errors. It's usually used for warnings because, warnings start with W. And so you're like, why is this? Well, take another example that's just slightly more complicated, right? And we have a function calling another function, this f with no arguments, calling this f with an argument. This example actually comes directly from the C++ standard, by the way. Some of the examples in the C++ standard are quite helpful, and I think many of them are, actually. We spend a lot of time crafting those examples as we write the standard, but we're not really writing it as a tutorial. We're writing it for compiler authors. But anyway, this first function is totally fine, right? It can be called in a way that would produce a constant expression, right? If we call this with false, it returns 0. That's something the compiler can do at compile time. But if we call it with true, it throws an uncaught exception, right? Which cannot be done at compile time. So because this second function unconditionally calls the first one with true, the second function can never be called, can never be used in a constant expression, right? Never produces a constant expression. And the standard says this is ill-formed, no diagnostic required, which is terrifying and a big problem. And actually, we're working on fixing that in this particular case. But it means that this program compiles fine, which means that this Constexpr here literally does nothing. So I guess that's the fourth meaning of Constexpr. It's nothing. It makes your program ill-formed. But that doesn't really have any real-world consequences because, this doesn't ever, we never try to evaluate this at compile time. If we ever tried to evaluate this at compile time, we get an error, right? Because the compiler can't evaluate and can't throw at compile time and not catch, right? Function templates work the same way, basically. All we have to do is add this template parameter to confuse the compiler enough to compile this, even though there's no way we could instantiate. There's no template parameter for which we could instantiate this, right? That would cause this to be a constant expression, right? So why is this ifndr? ifndr meaning ill-formed, no diagnostic required. And it's because we don't want to force compilers to solve hard problems, right? This is kind of an inverse problem where the compiler has to figure out all of the possible inputs. Now, for bool, it's obviously pretty simple, but if this were an int, right, then how does the compiler know without kind of exhaustively trying that, all of the integers it's tried so far, like 1 through 42, don't produce constant expressions, but maybe 43 does, right? So we don't want to force compilers to solve these inverse problems, and so we made this ifndr in the standard. That might be changing. I'll get to that in a bit. But basically, this is the summary of how ifndr is treated by compilers. The world's blowing up around them, and the compiler is just happy and oblivious and just lets it go. So let's get back to the original tweet. Why are we allowed to use assert in a Constexpr function? So if we look at this function that we just dissected, right, from the standard that the standard says is okay, right? We can actually call this, as long as we're calling it with false, we can put this in any of the places that it's required to be a constant expression, right? We can static assert with it. We can even initialize a type with it. And this to me is profoundly weird, right? Because if we had called this with true, this whole program wouldn't work, right? We're not really used to runtime looking parameters determining where we can call a function. But this is how C++ works. And that was something that was very surprising to me and that I learned from this. So if we look at how the assert macro is usually defined, it basically looks like this, actually, right? It's turns your thing into a bool. And if your assertion is true, it just returns 0, right? It's fine. Otherwise, it calls this function assert fail, which is hopefully pretty obviously not Constexpr, right? You can't assert fail. That's a runtime symbol. So assert expression is only a constant expression if expr evaluates to true. But that's exactly what we want, right? We want constant evaluated code to not compile if the assertion fails. And the diagnostic for this used to be horrific. It used to be like you never actually could tell that the reason why your code wasn't a constant expression was because of the assertion. It has gotten a lot better in the past, like literally year. Clang now basically says, your assertion failed, and that's why this isn't a constant expression, which is pretty useful. We are working on the ifndr. I don't have time to get into this more, but read this paper by Barry, or tweet Constexpr questions to Barry. he loves to talk about Constexpr and things like this. He can probably explain to you what a core constant expression is and why it's called a core constant expression and not an integer constant expression. Yeah. I'm going to move on. I think I'm going to skip. I didn't mean to exit full screen. I think I'm going to skip my second trick and dive into my third trick because I like that one more. I'm sorry I didn't get to the second one. I'll have to do it in another talk. This one, and I'm running out of time. This one has a lot of really interesting nuggets to it, and I thought it was mix in some good variety because it's a little bit more advanced than my first one. So I tweeted this around Halloween, I think, and that's why I said spooky. But this is essentially the text of the trick. The main thing I want to focus on in this slide, and I'll go through the rest in a second, is that we're creating this like global registry looking thing where we can call set with a template parameter, and then when we call get with the template parameter later, we get it back, and then when we can call set again, and then when we call get again, we get the thing that we set back, right? So we're kind of like, and this is cute, right? This is you can imagine a number of right ways to do this. I'm going to show you a very, very wrong way, but there's an interesting kernel of truth in here to learn about how lambda capture works. And I really want to get to that if I can, so stick with me. So here's a very simplified version of, not very simplified, but slightly simplified version of this trick. We've taken away the template parameters for a second because it's a lot less catchy this way, but this will explain basically the same thing. And I'm also throwing 0 instead of throwing success because I thought throw success was hilarious when I made the trick. But just to save some space and thinking. So what's going on here? Well, we have a set function that calls this impl function that's used by both get and set. And it calls it with its argument and then catches any ints that are thrown out of it and just ignores them, right? And we have in our impl function, right, when we call it with an argument, it stores the argument v, right, in a static variable that while it's initializing, the storage happens while it's initializing another static variable. And then, still in the initializer of that other static variable, we throw and don't catch it, right? So anytime we have an uncaught exception, right, we exit the current scope, right, and the function ends, right? So this line here is very clearly unreachable. I used a comma operator here for compactness, but really we could do this as an immediately evaluated lambda also, where we, say stored equals v and then throw, and then this line is clearly unreachable, but it's still determined, it still needs to be there in order to make this function properly return 0, right? It has to still have a return type. Properly return an int. So it still has to have a return type, right? And we're going to see that later in a second that we have an unreachable return statement that's still determining the return type of the function. So what happens when a static block local initializer throws? I went into much more detail on how this all works in my CPPCon talk. I don't have time for it now, but basically, C++ guarantees that these initializers will run exclusively by the first thread that gets there, and then the next threads will wait, right? If the initializer fails, then the next thread will try it, and the next thread will try it, and the next thread will try it until the initializer succeeds without an exception, right? Runs to completion without an exception. Since this one never runs to completion without an exception, just every thread that reaches here will run this statement and then get out of here, right? This runs with exclusive access to stored because C++ guarantees static initializers don't race with each other, right? For a given static initializer. And it also will always run because it never completes without an exception, right? And that's just summarizing what I just said. How are we getting the value back, though? That's the kernel of truth in this. That's really interesting. So line 4 is clearly unreachable because line 3 always throws, right? We've established that. But line 5 still determines the type of the function, right? The function still returns a lambda of that type. The type of every lambda is unique, right? That's how lambdas work in C++. It's a unique generated type in the compiler that we can't write the name of. But we can write the name of using decal type, right? We can say, this thing that you made up, right, compiler, I want to name that type. And if it doesn't capture anything, it's guaranteed to be default constructible, right? And we can just construct it, right? So here we've constructed that lambda that is returned there without actually ever having an instance of it. So we don't need to return it to make an instance. We just default constructed it. And because it doesn't capture anything, every instance of that lambda is equivalent, right? Static variables are not part of the lambda capture, right? This stored here is actually, notice that we're not capturing anything, right? This stored here is actually built, it's baked into the type and not any particular instance, right? So every lambda that captures, I mean, every lambda is a different type anyway, right? But the reference to this static variable is part of the type, not part of any particular value associated with that lambda, right? So we are able to, just by reconstructing another instance of the type, we are able to get access to stored without ever running line 5. And then if we just call that lambda, we get back the static variable spookily, right? Without ever executing line 5. The rest of the trick I don't have time to get into because I want to save time for questions. But basically, we're using template parameters as keys. And we can do that because every instance of a function template with different template parameters is different, and thus every lambda inside of it is a different type, and so we can reconstruct a different type pretty easily. And I will take questions now. Thanks for listening. If you don't get time to ask your questions or you think of one later, feel free to tweet them at me or email me, and I'll try and get back to you on them. Thank you so much. Are there any questions? I think I went over time a little bit, so hopefully that was understandable. Looks like Sai is going to come back in a second.
Hey,
Hi,
thanks
Sai.
very much for the talk. Oh,
Yeah.
God, that second example is horrifying.
It is horrifying, isn't it? I forgot to say, credit goes to Richard Smith for that. One of the cool things about working at Google, is that I get to work with people like Richard Smith, who were just absolutely brilliant, and like C++ wouldn't exist in its current form without him. And he came up with that, and I kind of just polished it into something that would catch people's eye on Twitter. Yeah, it's but the interesting thing about that example to me is that understanding how lambda capture works with respect to static variables is actually very important. It actually I can't name specifics, but there was a project at a previous place of employment that we worked with that literally that specific mistake or mistaken understanding cost them significant amounts of money because things weren't transferring to the GPU correctly because capture didn't work the way they thought it did. That's even if you give a default equals capture, right? There's no actual copy of a static variable. It's baked into the type, and so if that instance is on the CPU, then and you send the lambda to the GPU, you're not actually going to get it, right?
Yeah, for sure. Yeah, I like the way
that actually costs a lot of money.
I like the way you talked about Constexpr in the first part as well. Like, I always had the intuition that there's the different uses of Constexpr can sometimes mean wildly different things, but having it so clearly laid out is very useful.
Yeah, I wish I'd had gotten time to go into Const Int and Const Eval, because I think those are actually, we did the right thing there, right? We had two different keywords and we named them two different things. And they're pretty closely related to what we did. But yeah, thank you so much for the opportunity.
Thank you so much for coming along. Yeah. And that's us at time for this session. So everyone say bye to Daisy. And we're going to head right into the second session, to the third session, because we're right on time. So please welcome Mark, who's going to tell us about embedded development. Hey, Mark, how are you doing?
Hi, how's it going?
Good.
All right.
Glad that we are on time. So take it
away.
Great.
And it looks like things are working, sharing the screen and stuff, so I can get going. Yeah, so my name's Mark Goodner. I'm a program manager on the C++ team here at Microsoft. And I'm here today to talk about Visual Studio and VS Code, using those for embedded development. So just kind of to go through what I'm going to talk to you about is kind of why we're looking at embedded developers, or why we're working to improve Visual Studio and VS Code for embedded developers, the approach we're taking, where we're at today. Then I'm going to give you a quick demo of using, I'm going to show VS Code today, of doing some embedded development with that, so live demo. And then I'll talk a little bit about what's next, and then we'll have time for some questions, hopefully. So just as kind of a preview to show you where we're going, this is a screenshot of Visual Studio with most of the embedded features lit up. So you can see there's a peripheral register view there. Down at the bottom, there's a view of RTOS threads. So we've got RTOS awareness, and kind of the same view in VS Code. So we're trying to maintain parity between VS and VS Code of the features that we're enabling for embedded developers. So why do we care about embedded developers? One of the big reasons is actually Azure Rtos. This was a product previously known as ThreadX. You'll still see it referred to as ThreadX a lot. But this is a real-time operating system that that Microsoft provides for microcontrollers. So we previously didn't have something this low level. But now that we have something that's low level that runs like on Cortex-M processors, we need to be able to provide a end-to-end developer experience across our own tools, because a lot of embedded development occurs outside of Visual Studio and VS Code. There's a lot of proprietary IDEs out there, or vendor-specific IDEs or tool sets. But with ThreadX, having Azure Rtos as a Microsoft first-party experience, we wanted to be able to give a first-party story across our development environments, and full support for those. Another reason we care about embedded developers is they're a very large C++ cohort. So there's a lot of embedded developers out there that use C, C++, and it's kind of one of the last markets we haven't really spent time on in our C++ support for Visual Studio and VS Code. And they have unique core inner loop needs. The embedded developers, the needs that they have for their development in terms of like edit, build, deploy, debug are different, because they're really working close to the hardware. So their needs, there's the core, a lot of the core standard C++ functionality of VS and VS Code accrues to these scenarios, but we need to do more for embedded developers so that they have a good working environment. There's also some interesting problems embedded developers have. The acquisition is really painful for embedded developers especially. It's a common pain point across C++ that it's difficult to get your tool sets set up and all of the libraries and everything that you need. But for embedded developers, it's especially hard because there's cross compilers. The cross compiler is often set for a specific piece of silicon. You have to go to a specific place to go find it, all of these sort of things. So we wanted to try and take a try at trying to solve some of those problems. So how are we approaching this? The first is we're trying to commonly solve those core inner loop needs across VS and VS Code. This is kind of an internal point to us, but you'll see it reflected in when we talk about VS or VS Code you'll see a lot of the same functionality. It'll look the same. And that's because for us, we're trying to write once as much as possible and have it working in both environments. And so, today we're focused on some of the core needs for embedded developers in that inner loop. And one of those is peripheral registers, being able to access things like the GPIOs on the device, on the microcontroller, and being able to see what those values are, interact with those values, having a semantic representation of those. This is something that's not as common for desktop developers, but microcontroller developers really need that. We also are providing a view for Rtos objects. So for ThreadX and also for FreeRTOS, we're giving a view of what those objects look like. This because an Rtos gives you an ability to manage tasks across the Rtos in a way that kind of virtualizes threads, even though you may only have one thread available on the microcontroller. But you want to see the representation of all of the tasks running in the Rtos and see what their states and values are. So, and in terms of acquisition, we're really trying to solve acquisition not only for the IDE, but also for CI, because you need a reproducible build environment for your projects, of course. And that should work for your IDE and it should work for CI. So what we've done is we've added artifact capabilities to VC package. This is an ability to express, I need ARM GCC, I need an OpenOCD debugger, these sort of things that get described in a manifest that you can check in with your project. And then that will pull down the bits if you don't have them, put them on the command line and make them available for use. And we'll see more of that in the demo. And the other thing we're working on, and I don't have a lot to dive into in depth here, but we're working closely with silicon vendors. We really, in order to be successful here, we really need silicon vendors to be able to recommend the VS family of IDEs to their customers. Otherwise, their customers won't hear about this. And so we're working on with them as well through adoption of VC package so that there would be registries available of the tools that come from the silicon vendors available to embedded developers to use in their solutions. And then, of course, we've also got to work with the silicon vendors around how can we, in the future, start defining new project experiences that include the device configurations that are necessary for embedded development. And so where we're at today, we have a peripheral register view that we're going to show, and we have an Rtos object view for Azure Rtos and for FreeRTOS. I'll talk at the end about where we're going next because we have more coming on that. And then we also have some example projects already pre-configured for you for Azure Rtos. These include the debug configurations and VC package manifests, so you can see how all of this works together. We have one for an Azure Iot Dev Kit, which I'll be showing today, which is kind of a sample dev board. This little credit card guy that has sensors and stuff on it for use. And then we also have one for NXP and for ST Micro. If you can take a look at the configurations for these and kind of see how those are set up, I'll walk through a little bit of that in the demo and adjust it to your own needs. And then the other thing our team did last summer, we had an intern on our team who worked with the Wsl team and an open source project to bring USB IP support to WSL2. That enables you to share your microcontroller from your Windows host machine into WSL, and I'll be trying to use that today. And so in terms of setting up for Visual Studio, when you install Visual Studio, our embedded capabilities were introduced in 17.1. And in order to use them, just install the Linux and embedded development workload. And the options for that are pre-selected, the embedded IoT tools right there. And for VS Code, search for the embedded tools extension. That will pull in all the other necessary dependencies that we have, like the C++ extension in VS Code. All right, so let's do it. Let's try and take a look at what this is going to look like. This is how easy it's going to be to get an embedded project going. But first, I want to go to my administrator window here. And what I want to do is show you USB IP. So USB IP is a utility here that I can actually share a USB device over USB IP and then connect to it from a USB IP client. And that's how we're bridging from the Windows host into WSL. And so what I can do is take a look at what's on my machine. And you can see here, the one I'm interested in is this ST-Link debug. This is my little dev board that I showed earlier. And this program has a helper function, WSL attach, because in order to share something with USB IP, there's a lot of commands you have to run on the client side as well on the host side. And this command automates kind of on the receiving side because WSL is local on my system. So we can just run this command and attach it in there. And I can show you, this is my WSL system. You can see there's only the root USB hubs represented there. But if I run this command, then what's happened now is if I run lsusb again, now this device is shared into my WSL environment. And if I do the list again, you can actually see that it shows that this device is attached. So let's go to our Getting Started project. So this is a GitHub project that I cloned. Links are in the deck. And what this project has in it, this is a pretty basic project for a ThreadX project. So I've got my source code, I've got my CMake set up, but I have this VC package configuration file. And so if I take a look at this file, what you'll see is that there's a registry. All that's at this registry is JSON files that describe the artifacts that are available. And so here I've specified that I need ARMGCC, I need OpenOCD, I need CMake and Ninja to build my project. And so the registry doesn't contain the bits. The registry contains metadata that says where to go get those from. So when I use this, it's going to go get the compilers from ARM, it's going to go get the OpenOCD from our build, etc. And so if I say CMake version right now, you'll see I don't have CMake on the command line. But what I can do now is just source VC package. So this is a .source script. So now I've got VC package available on the command line. And all I have to do is say VC package activate. And this command is going to read that manifest file. And if I don't have these tools installed, it will go get them, pull them down, and put them on my system, and then activate them for use. So now you can see that all of these tools, it went quickly because I've already installed these before. But now if I run CMake version again, you'll see that I've actually got 320 available on my command line. So now from this activated environment, I can start VS Code. Give this a little bit more room here. And so now this is coming up, and now my project is activated. I've got my compilers available to me for the for ARMGCC, and Intellisense is working. So if I can search for button, you can see now I can actually navigate down here to a callback for pressing a button on the board. I've got a breakpoint set here on this line. You can see Intellisense, hovering over this value shows me that this expands to a register. So this TEM3-CCCR1, this is a peripheral register. And so what I want to show you is how I can actually inspect that and see that value working. And so let's see, now I can go ahead and launch this. And so this is running in the WSL context. You can see here that WSL is set, but it's actually reaching out to the device over USB IP that's actually connected to my Windows host computer. And what it's doing now, it's flashing the device. And so you can see on entry, we break, and that actually pulls up our assembly file that's part of this project. So this is our startup assembly file that's very common within embedded projects for your startup. And I can go ahead and step around through this. I can also, from the call stack, I can right-click and open a disassembly view. And so I can even step my disassembly. So this is pretty great. These are pretty common tasks for embedded developers to need to go down to this level. It looks like I've got some rendering issues from the screen size I've got here. But let's go ahead and continue. Now I have a breakpoint set there, and if I press the button on the board, that's going to trigger my breakpoint. And it's hard to see here because it looks like I've got some rendering errors with the size that I have. Let me see if I can shrink this down a little bit. There we go. All right, so if I scroll down and I find this TEM3, this is the general purpose timer register that we were looking for. And then we can see CCR1 was what this is set to. And so now if I step over this, you'll see that that value updated. So this is useful to embedded developers because often they need to check what's going on the peripherals attached to the hardware and making sure that their code is doing the things that they expect the code to be doing. Another thing within embedded development that's interesting is hardware breakpoints. So you don't have infinite hardware breakpoints. So we've got 4 or 5 breakpoints set now. Now I've got 6. Now I've got 7. And you'll notice that this one set is gray. That one set is gray because we only have so many breakpoints available to us on this board. And so what would happen if I didn't respect the number of hardware breakpoints on the board is I would try setting another breakpoint, and then it could corrupt the state of the debugger. So we actually have support for monitoring that so that you can unselect another breakpoint and then set the one that you wanted. So that's another useful thing that we've got. And before I forget, here's our Rtos Viewer. And here you can see all of the tasks that are running as part of the Rtos. And you can see things like, how many times these tasks have run, where the stack pointer is, where the stack ends, what the stack size is, and also what the maximum usage on this stack was. This view changes a little bit from Rtos to Rtos. This is what it looks like for ThreadX. For free Rtos, it would look a little bit different based on the values that are available. And so I'm going to go ahead and stop debugging. And if I show you one other thing here, in this folder in the launch.json, you can see this is our configuration that we were using to launch. And you can see here that we're configured for, we're just running on the command line for our RMGDB debugger. But the important part is here is the debug server path and server args. This is something that varies depending on whether or not you're using OpenOCD or Segur. We have Segur examples for our NXP board, and then the parameters that you pass for your specific board. And so this is something that's going to vary board to board in terms of what you need to pass in order for your specific board. And here's the hardware breakpoints that I mentioned. So this particular board has a limit of 6, but that also varies board to board. So let's get back to the presentation. All right, so that's it in a nutshell. You can just clone a repo down, go into your repo. I didn't show the install of VC package because I already had it installed, but we have a one-line installer for VC package. That's what it looks like on Windows. And then once you have VC package available, then you can just say VC package activate when you have a manifest. And it will pull down everything that's necessary for the project if it's not already there, and then activate it for use. And then you can launch VS Code, or from a VS Code or Visual Studio command prompt, I should say, you can start dev-in, and everything's available to you, and you've got a complete Bootstrap Linux and complete embedded environment available to you. That's the one-liner for Linux, that's PowerShell, and that's command. All right. And just kind of for reference, as a reminder, if you ever find these presentations, this is kind of an example of what the manifest looks like. And just kind of in review, this is the peripheral register view. This is the screenshot from VS Code of a before and after of stepping that value. And then we've got our Rtos object view. This is what it looks like in Visual Studio. So very similar view, but themed for Visual Studio, using Visual Studio functionality to get the same view there. So in review, we've got our core inner loop set up for embedded development for edit and build. We can debug on a device target. We have peripheral register view available now, and Rtos object view. And we're setting up our reproducible environments through VC package. And where we're going next, we're continuing to work on partnerships. I hope that there could be something more public to say about that, hopefully around embedded world, which would be in late June. And we're continuing to make improvements here. So continuing to focus on our Wsl support. This is something, the demo I just showed you using our extension in Wsl doesn't work with the release version today. We have an RC that's posted on our GitHub that you can download that has the Wsl support as part of it. That RC also has Zephyr support, so we've already gone further to add another Rtos view support for Zephyr. And one of the next places we're going, not part of our RC, but we're also working towards getting VC package integrated as part of Visual Studio and part of Visual Studio Code, so that you don't have to activate from the command line and then launch your IDE. Instead, we'll have, when that manifest is there, just activate within the context of the IDE. We're also working on a serial monitor. The word monitor is there, but it does support input. So that's something that you'll see in Visual Studio 17.3 when that first preview comes out soon. And then we're also working with CMSys. So we're hoping to start leveraging CMSys to get things like the SVD file for rendering the peripheral views, helping us to understand how to automatically configure for debug, and all of those sort of things. Don't have a lot of time to go into this, but I didn't talk about makers at all. Our team actually does own the Arduino extension that's available for VS Code. It's not a deep area of focus for us, but it is something that we do care about, and we do keep this extension current. I don't know a whole lot about where we're going to be going for the future of this, because we're more focused on professional embedded scenarios around RTOSs right now. But we're also looking at the Raspberry Pi Pico. We've been doing some experiments on getting the Raspberry Pi Pico SDK to work within the context of VC package. So that's something that should be coming soon. And then we can probably freeze this slide or take a screenshot of this. This is a link to all of the announcements on the C++ blog about the capabilities that I've shown. And that's my contact information if you would like to reach out and learn more. And I think that's the end of the deck there. Let's see. Oh, I went really fast.
Yeah, thanks very much. Don't worry about it. So we've got a couple, well, one comment and one more of a comment and one question. One question is Azure RTOS C or C++?
I believe it's C. I always say C++, but the embedded world is largely C.
Cool. And then the more of a comment is, in my opinion, for embedded development, VS needs a piece of software which can be connected to and read from embedded system and read from embedded systems automatically. Get the VS Code could have some extensions for this, but at some point you wonder if there's too many extensions to the point that becomes difficult and out of your way to work with VS Code and not another piece of software. What are your thoughts on that?
I don't know how to think about that one. That's almost kind of a difference between Visual Studio and VS Code, I think. VS Code is really built to, all of the capabilities come from extensions. It's unlikely that we would take and put all of this core functionality just directly into VS Code with no optionality. There's ways that you can express extension dependencies as part of metadata that go with your project for VS Code, particularly with dev containers. For Visual Studio, that's much more the case in Visual Studio, that things are all there. You select your installation options, and then you get things as part of the install. And so the embedded workload in Visual Studio is something that we're intentionally not delivering as an extension. It's actually part of Visual Studio.
Cool. Feel free for other folks to drop questions in the public chat. We've still got a decent amount of time. So you mentioned Arduino and Raspberry Pi. So
yeah,
like my kid has been interested in some coding things. Do you think Visual Studio Code with the Raspberry Pi is like a nice experience to get going with something like that?
Yeah, so VS Code, actually, you can run that on a Raspberry Pi. The thing we're looking at with the Raspberry Pi Pico SDK I mentioned is the Raspberry Pi Pico is a little microcontroller from Raspberry Pi. It's not the full, single board computer that is the regular Raspberry Pi. And their SDK is a little bit difficult to bootstrap and get running. It's not too bad on Linux, but particularly on Windows, it's a little bit more painful. So this is something where the acquisition strategy from VC Package can help, because we can just express that dependency, pull that SDK down from Git, and then have all of the other system dependencies expressed as part of a manifest, so that you don't have to go through the manual and go through like 5 or 6 pages of just setting up installation options before you can get going. Yeah. And
I wonder if that would be useful for, like, on my desk, I've got a Synology NAS, which runs an Atmel chip, and like I've cross-compiled things for that myself by just pulling down the GCC toolchain and sometimes completely hacking something to get it working. But do you think that like VC package artifacts and VS Code would be a nice thing for targeting a system
I think
like
so.
that?
VC package artifacts is going to go a long way to helping with cross-compile scenarios like that. I mean, that's really kind of the core place that we started with the artifact work. I mean, we're expanding the artifact work to cover C++ more generally. So we're working on being able to activate MSVC via VC package, for example. So the scenarios there, we care about desktop, and we'll be expanding that to cover desktop scenarios as well.
Cool. Yeah, that sounds good. Anything to make that easier? Like I remember trying to compile Nginx with their RTMP module for my NAS, and the whole experience was not very fun.
Yeah.
Cool. Well, thank you very much. I guess we'll see you later, Mark, and we'll move on to the next session. So we're running a little bit ahead of schedule now, but these things out, we should be fine. So our next session is going to be static analysis and program safety with Sunny. Can we get Sunny up? Hey, how you doing?
Hey, Sai, I'm doing great. How are you?
Yeah, good. Looking forward to the session. I think static analysis in editor has been a big thing for me in terms of just having something there running, telling me what I'm doing wrong while I'm coding. So I'm interested to see what else is new. So I'll hand it over to you.
All right. Yeah, it's great to have your friend telling you all the bugs even before you have committed your code. So I think static analysis is a great way to find bugs early. All right. Hello, everybody. My name is Sunny Chatterjee. I am an engineering manager in the Visual C++ team at Microsoft, where I'm lucky enough to lead the static analysis team. And today I'm going to talk about everything that I learned working on static analysis and C++ program safety over the last several years. I'll share a lot of learnings with you. So let me get started by going into why C++ code safety matters. I'm going to start by quoting Bjorn on this. Last year in CPPCon, Bjorn did a talk on type and resource safety in C++, and he had a paper as well on it, where he mentions that complete type and resource safety have been an ideal aim of C++ from very early on. So at Microsoft, we believe that great customer experiences, they start with quality. You can write a feature that is, you can ship a software that is loaded with features, but if the piece of software crashes or hangs, if it has poor performance, or if it has security vulnerabilities, it's unlikely that people are going to love that product. And it turns out that you need more than the language and the compiler to be able to write great software. You need some judicious programming rules that you get from the C++ core guidelines. For those of you that haven't checked this out, it's available in the ISO CPP GitHub repo. You need a guideline support library to enforce some of the guidelines through type extensions. Microsoft maintains its own guideline support library in GitHub. It's an open source project where we welcome contributions from the community. You need static analysis tools to enforce the guidelines and find defects early, even before you have committed your code. And you also need good dynamic analysis tools. For those of you that haven't checked out, do check out MSVC's address sanitizer. And you need runtime checks to be in place in case you have introduced some security vulnerabilities in shipping software. You do want to cater to them at runtime. So for today's talk, I'm going to focus on the first three topics, which is core guidelines, guideline support library, and static analysis, and how we have been using these to make C++ safe. So before I head into the specifics, I want to talk about what is static analysis. So let me start by sharing this article from The Economist that came out almost a decade back. It's called Building a Better Bug Trap. Essentially, it talks about a bug which costs $1 to fix on the programmer's desktop would cost several hundred once that bug is incorporated into a program. And it will cost many thousands of dollars more once the bug has been shipped with your software and that software has been deployed in the field. This is where I think static analysis becomes extremely important because it finds bugs in programs at compile time. What it means is that you will find these issues even as you're typing your code, or you're building, or you've say spun off a PR code review, and you will find these bugs at your fingertips. It applies some clever techniques to look for specific bug patterns in your code. And it's a complementary technique to traditional testing and runtime checks. It's not a substitute for them. Saves a bunch of dollars for the company, which large corporations love. So let me give you an insight into how we have integrated safety checks in the shift left experience for developers. I'll first start with our native Visual Studio experience. So this is a snapshot of Visual Studio. So every line of code that I shared today has been picked up from some production software that we have looked at. So in this particular example, you will find that Visual Studio has pointed out some green squiggles in the code. Specifically, I would say that one of the objectives for us was to make sure defects show up in almost real time as green squiggles as you're typing or saving your work. And defects should be easily understandable. And there are a few highlights down below. Let me double click on that. We have this feature called key events that shows up in the error list. It basically gives you the thinking behind the analyzer, why the analyzer believes there is a bug here. So for this particular example, the analyzer is complaining that P context can be null. And it gives you the reasoning why it believes so. So if you follow the reasoning, like line 70, it's initialized to null. On line 18, the branch is actually entered. The not P connection is assumed to be true. So P context is never initialized to anything other than non-null. And then on line 26, you are dereferencing that, which results in a null pointer dereference. My second slide would give you an insight into how we have integrated these same checks on GitHub. So if you are working on GitHub, we have a GitHub security action where you can go to your C++ repo. And if you are working on CMake-based projects, you can go to the security tab and go to the code scanning alerts. And you can set up code scanning for your repo. When you select code scanning, there are a bunch of code analysis actions or code safety actions that you will find. There's one from my team called the Microsoft C++ code analysis action. And you can click on that, set up this workflow, and it's configured for your repo. Here is an example of the same code. When I ported that over to GitHub, you now see that that warning in the GitHub visualizer. And there are a couple of interesting things happening here. You find this warning embedded in the same way like regular user comment in GitHub, if you're familiar with that. It shows you dismiss box here where you can dismiss this warning and mark it as a won't fix, or you can fix this warning and resolve it. There is another interesting box here called show paths. And if you click on the show paths, it basically gives you the same reasoning that you just saw in Visual Studio in the GitHub. It brings up a separate window where you can follow the reasoning of the analyzer step by step, why it believes there is a bug in the code. So we believe that this kind of experience is an ideal way to shift left because you now have an action for the whole C++ community that's publicly available. You can go read about this action in our team blog, where we blogged about it around last CPPCon. If you want to learn more about code scanning in GitHub, you can go. You can maybe take a snapshot of this slide. I have given some links here. There are you can view results in the GitHub visualizer. You can easily integrate your own analysis tools because it's all driven off a standard static analysis log format called Sarif 2.1. It's a standard format based on JSON. And as long as your analysis tool produces that format, it's super easy to integrate into the code scanning alert in GitHub. So if you are a maintainer of an OSS project, give this a try. It's free for all public repositories. And as you saw, it automates running static analysis in the PR workflow and surfaces all the results to the engineers before their code is merged. If you are working on a private repository, you can read more about the offering from GitHub Advanced Security page. And most recently, we have also integrated static analysis in the Compiler Explorer. You can now select the latest MSVC tools drop and select static analysis from the tools menu. And we have seen that Compiler Explorer is a great way with which we interact with developers. Like, it's great for getting repros back with a small tiny URL. It's also a great way where developers can try out our latest offerings, the latest checks that we blog about. So I'm excited about the fact that people can now quickly try out these checks in Compiler Explorer before deploying that in production environments. So you can find that the same warning on that code now shows up inside of the Compiler Explorer. So next, I'm going to switch my focus into the learnings and evolution of running static analysis. So a lot of what I share today will be real-world code in production software. And I want to keep the authors of these code anonymous. So for today, for the rest of the talk, Peppa is going to be my author. So there is a cute little picture of Peppa Pig on the right-hand corner of my slides. And let me just start with the very first days of running static analysis at Microsoft. So we started with lint style checks. What lint style checks are, they are basically checks that find defects quickly. These defects are pretty cheap to locate and fix. And these are built on syntax trees or simple, slow analysis. And there have been many successful lint checks that are available in the market today. So we have a bunch of happy customers using this lint style checks. So let me give you examples of what these lint style checks look like. So here is an example where, again, it's like a piece of code from production software where you have a function foo and something funky is going on in this function where X is a union. I've just defined X as union containing two pointers, one to a void star and one to a y star, where y is a different structure. I don't have y defined here. But there is something going on in this line that I have highlighted in red in this function. Let's check out what's happening here. Let's start from the beginning. So on the very first line highlighted in blue, we allocate a new union object X, assign it to this px. We assume that condition to be true. So we are reading in a string from an external stream, and we are assigning that string to the PV field of the union, which is a void star. And way below in the code, we forget that the valid field of the union is PV, but we forget that, and we end up referencing the field PY of the union. And that ends up calling a function f, which is essentially fed by this string. So an attacker can easily control the function that you are calling in this particular case. And that's a pretty nasty vulnerability. So it turns out that you can write a very simple lint style check to identify patterns like this in your code. So you can inspect the syntax tree and say that, hey, whenever I see a union that uses multiple type pointers, it can cause this kind of type confusion attack. So I'm going to forbid that in my source code. So here you can see there is a warning that says, don't use a union with multiple type pointers, use a variant instead. And that is, in fact, also a specified rule in the C++ core guidelines. Under the type safety profile, there is a type.7 rule that exactly asks you to do that. Now, it's a simple lint style check that came to the rescue, and Peba is pretty happy about that. She can prevent new code from having the same kind of errors in her code base now. So what you just saw in the previous example is a type confusion attack where unions with multiple pointer value are vulnerable, especially when one of those depend on external conditions. You can easily lose control, and it's remarkably common in production software. Mitigation is also pretty simple. You basically ask programmers to use a stood variant instead of these naked unions. And by writing a lint style check and enabling that check in your inner loop, you prevent new code from having the same defect again once you've fixed it. And it's also supported by the C++ core guidelines. Let's look at a next example of another lint style check. Here, getIndex is a function which takes a pointer to an integer and called buff and an integer buff size. And our interesting function is fetchElement, which also takes pointer to an integer buff and an int buff size. And we call the getIndex function and return the buff index. So essentially, it's basically reading into a buffer. So let's see what happens when we run static analysis on this code. We get a warning saying that symbol buff is never tested for nullness, and it can be marked as not null. The reason static analysis gives you that warning is because it figures that for buff index to be a valid access, which is a dereference into a buff at an index offset, it should be non-null. However, it cannot prove that buff is not null. Its nullness is unknown at the point of dereference. So it tries to enforce that star buff the index to be valid operation, buff must be not null. And it's asking the programmer to specify that in the function. So it's an easy bug, but often difficult to track down later. But you can see here that it's easy to determine these bugs with simple flow-sensitive analysis. So what Pepa does here is she goes and adds a null check. She checks the buffer to be non-null, and then she does the access into the buffer. And that way she has been able to safeguard against the null dereference issue here. Again, this proves that lint style checks are easy to locate and cheap to fix. So let's look at the next challenge. How can we scale these lint style checks? That's been our challenge. So there are the lint style checks are great in finding simple to detect errors in your code by looking at the syntax trees, doing simple control flows, but we need to do more. We need to analyze across the function boundaries because we want to get a full overview of the program to be able to find deeper bugs, deeper semantic issues in the code. So there are two ways to do that. One is the interprocedural analysis, where we often call it as a whole program analysis, where we start with some leaf level functions, we try to build the function properties, then we propagate that across the call chain. Because we are doing a lot of work here, this kind of analysis is slow, and for a large production code base can often take days for the simulation to run. So this kind of analysis is ideally suited for the outer loop. Like once code has been merged, you can run this kind of analysis in the outer loop and file bugs that developers can go back and fix later. Again, it's great for specific problem domains. Like we have very successfully run a global analysis tool at Microsoft called Prefix, which was great in finding use after free class of errors. There's the other approach to doing whole program analysis, which is called intra-procedural or local analysis, where we try to analyze across the function boundaries and we look at each function in isolation. The challenge for us is we can't see across function boundaries, but we try to infer the semantics of the calls by looking at several different properties. Like we can look at the types of the parameters, we can look at the types of the function return type, we can look at type extensions. So for those of you that are familiar with Microsoft's implementation of the guideline support library, we have a bunch of type extensions there called the Gsl Span, or we have a Gsl not null. So we can use these type extensions. We look at modifiers. So if you have a const modifier, for example, to a pointer parameter, the tools can assume that chances are that pointer is not going to modify the data because it's marked as const. We can use heuristics. If we have nothing but a raw pointer to a pointer parameter, the tools can assume that maybe it's reasonable for us to treat that pointer as it's maybe readable from and writable to, because there is no modifier on that. We can assume that to be an in-out in its semantics. And we also put in a bunch of source annotations. At Microsoft, we have been using Microsoft Sal for a number of years, where we can describe properties of the function contract in a formal way. And these source annotations have been great in bridging the gap between local and global analysis. So we can convey the behavior of the function call to the caller by using these annotations. This kind of analysis is pretty fast. Like you can get results order of milliseconds or seconds. So it's ideally suited for the loop. So you can run it during your development, you can run it during the PR. Essentially, you can find bugs using this kind of analysis before your code gets merged. And it can find issues across a wide range of problem domain. So our focus for today will be on the intra-procedural or local analysis, where we analyze each function in isolation. So let's look at the same previous example that I showed you for the lint style checks, the same example. And you saw that Pepa, our programmer for today, she added the null pointer check on the buffer. And she ran the static analysis tool one more time. And she found the different warning this time around. This time, the analyzer issues a warning that says buffer is, there is a possibly incorrect single element annotation on the buffer. So buffer is assumed to be of 1 byte in length. And so there is a potential overflow when you're using the expression buff index. Now, this is confusing because paper does not know why the analyzer believes that buff is of size 1 element, because there is nothing here that says that. And so what paper does is she goes and does a search for all the callers of the fetch element, and she realizes that buff is not of size 1 element, but all the callers make sure that buff is at least as large as buff size before they call fetch element. So the buffer size here is not 1 element, but of buff size element. For anybody looking at this function in isolation, it's very difficult to figure out how that pointer to an integer parameter and that integer buff size, they are related just by looking at this function. So once Pepa convinced herself that yes, this buffer is of in fact buff size and not 1 element, she had the next challenge, which is how do I express that? How do I express that in C++? Because C++ does not really allow you to express buffer sizes. So the challenge for Pepa now is how to express buffer sizes in C++. So she magically chances upon this header in the Windows SDK called sal.h and figures out these cute little annotations. One of those annotations is called inReads, and it is exactly what she was looking for. Here, inReads buff size essentially tells the analyzer, hey, buff is of in fact buff size and not 1 element wrong. So Pepa uses these annotations in her code and reruns analysis, and then she stumbles upon something else. She gets a new warning from the analyzer that tells her, hey, there is a potential read overflow happening here using the expression buff index. And the analyzer tells that the buffer is actually unbounded by the buffer size. In fact, in particular, the result from the get index function call is not constrained by the buff size. This is in fact an actual potential buffer overflow that's been found, because as you can tell, get index can return any size t. It may not be bounded by the buff size. So if you just use that blindly without checking that the index is bound by buff size, you will end up accessing the buffer out of bounds. So using this sal, we were able to find this real buffer overrun in the program. So Pepa is somewhat happy that she's found a real bug before it escaped to the hands of the customers, but now she's debating whether she has to learn a new annotation language and these cute little esoteric notations. And so the challenge for us is, before we solve the next challenge, I just want to touch upon this, like advantages and disadvantages of this annotation-based approach. So annotation-based approach is great for formalizing your code documentation, improves static analysis, gives static analysis tools a chance to read these in a formal way, improves the API design, because you want to be able to express the contracts of your API so that the callers can use these APIs in the right way. So you can think of annotations improving the design of the APIs, and it provides a lasting and incremental return on investment. As you add more annotations to the more vulnerable parts, buggy parts of your code base, you get benefits out of that right out of the bat. That said, there are several disadvantages to using annotations. They are non-portable. If you're working across different tool chains and sharing code, you can't port these annotations easily. They're viral in nature. They would quickly explode in the source code as you propagate them across the caller-callee chains. And they're not the ultimate source of truth, because if your code evolves and if your annotation has not been updated, then the annotations can quickly go stale. And it's only as good as the tools. If the tools are not able to make sense out of the annotations and take advantage of them, then there is no point in spending efforts annotating your code. So the challenge here for us was, can we do better than SAL annotations? And the next slide gives you an answer to that. We worked on this type called Gsl Span Type, which is available as a type extension in the Microsoft Gsl library in GitHub. In C++20, we also have this in the most C++ standard form called the Gsl Span. And what Gsl Span encapsulates is a pointer parameter and its extent in a single encapsulation. And it does not have its own memory allocated. It's just a view over a contiguously allocated memory. So anytime you're passing a contiguously allocated memory, if you use this Gsl Span Type, what it does is it automatically provides that beginning pointer and size information to the tools to figure out buffer overruns at compile time. Not just that, it also gives a chance to the runtime checks to also verify that the buffer that you are accessing is within the bounds of that span, because as you pass the span, the extent of that buffer is always known to the compiler toolchain. So by using the span type, Pepa has now finally able to use a type that is range checked at runtime. So even before that if guard that you see here with my blue arrow, this code is safe. Without the if guard, we would want statically saying that index is not bound by the indexes will not be bound within the sizes of the buffer. But even if you forget to add that if guard, your code is safe at runtime because you now have a way where the runtime can check that if the access is within the size of the span, and if not, it can terminate your program. So type and type extensions are really great because first, they are portable. They can work across different tool chains. They are checked by the compiler. And suddenly, runtime checks become possible. So even if you've managed to ship software with some security bugs out there in the field, you will find that your runtime checks can add a layer of safety. So Pepa is happy because she's now seen these modern C++ types and discovered that these types and type extensions are a great way to write safe and reliable C++. With that, that brings me to the end of my learnings by working on static analysis over the years here at Microsoft. And with that, I'll leave you with a number of ways you can join the fun. As you've seen, code analysis finds bugs. It's free, and so you should use it. If you've not seen these tools integrated into your developer environment, and if you happen to have an engineering systems team, talk to them. Make sure that code analysis tools are part of your shift left experience, where you type, build, and create PRs. Why should you use it? If you're not convinced already, I can share some anecdotal experience that I did in the past few slides. Been in use at Microsoft for nearly 2 decades. There have validated millions of lines of code in production software. Static analysis technology has evolved over 10 years of it has over 10 years of research into it. It's available in all editions of Visual Studio. It's available in GitHub Actions, Compiler Explorer. Internally at Microsoft, we have a few tools called OACR and Guardian. So all of them have static analysis integrated into them. And it's also a US executive order regulatory requirement here at Microsoft. So in March, we did a big security push by fixing static analysis bugs. We actually fixed about 1,000+ bugs in Visual Studio Codebase in March. So what's next for the team? We want to invest into more and more safety checks. It's our mission is to make sure that C++ is a safe language to use, and we have been making efforts to putting out checks there that will find some of these bugs in real time as you type your code. So we'll revise the buffer overrun checks because the current implementation is somewhat noisy. There is null pointer dereference that we are improving. We have been working with the security team at Microsoft to detect arithmetic overflow in allocators. And that check has been very successful internally. So at some point, we'll likely put that out in the open. We have been writing checks for determining memory leaks, pointer safety, stud optional exploits. Our lifetime checks are experimental. We do want to move that out of experimental into production ready state. Also do check out our Microsoft GSL repo, where we work on these type extensions and interact with the community. We made a release at the beginning of the year. So we have a blog about GSL 4.0. We want to support new language features. We want to make sure that as new language features get invented, like coroutines, for example, you have new ways of introducing bugs. Like with coroutines, you can run into lifetime issues. And we added a bunch of static analysis warnings that will detect these lifetime issues when you're using coroutines. With modules, we want to make sure that the static analysis artifacts are exported and imported across the module boundaries. We also want to create static analysis tooling around modules, and there will be upcoming announcements in the next few months on that. We are also, looking closely at the C++ code contracts proposal that's under consideration. Our hope is that some of the functionality, one of the nice things about SAL was its extensibility and its composability and its expressiveness. We want to make sure that if there is a code contracts proposal that's being worked on, it meets the needs of SAL so that we can replace some of our custom annotations with standard code contracts. We also want to evolve SAL against that backdrop of, as code contracts become available in the language, we want to evolve our guidance around SAL usage, both internally and externally, and move to a more standard portable implementation. We want to improve the accuracy of the results because as these checks get integrated into the inner loop, it's extremely important that the noise to signal ratio is improved. We've been working consistently on improving the performance. So last year, we worked a bunch with the OS repo here at Microsoft, and we sped up our checks by 45%. And there is a lot of concerted effort that went into it, a lot of heuristics, like if you have been filtering out certain locations, we are not trying to build these expensive control flow graphs. We are not trying to do path-sensitive analysis, which are time-consuming. So we added a bunch of heuristics to make sure that these checks are getting faster over time. We want these checks to be more understandable. So key events that I showed you at the beginning is a great example of that, where you saw that you're not only getting that warning when you're typing in your code, but also the analyzer is dumping out its reasoning. Why it believes there is a bug. We want to customize the results of analysis. So there have been a bunch of features that we have already shipped, like the /external. It's not an analysis-specific feature, but it's for all compiler warnings, you can configure your environment such that maybe you don't want to address the warnings from external headers. So /external flag does just that. We also have rule sets by which you can configure analysis warnings, and we're trying to modernize that experience, making it more intuitive and easy to configure rule sets that is custom to your project. And we are trying to evolve this notion of defaults depending on the C++ target that you're choosing. You can't have one default for every kind of C++ software that you write. So we want to make the default smarter. And we also want to invest in filtering the results. Like the GitHub experience is our first start there, where you saw it's very easy to filter results that is shown in the GitHub visualizer. You can filter results easily there. And we want to add similar capabilities in the native Visual Studio experience as well. Our North Star goal is to make static analysis universally available. One of the things we do realize is when it comes to static analysis, the tooling experience is inconsistent across the tool chains. You don't get the same kinds of checks across different tool chains. And so one of the projects that we are investing right now in is to see how we can modernize our ASTs, which are the building blocks of analysis, and create this an intermediate program representation that is more stable than the underlying compiler. I'm hopeful that in the future we will be able to create a shared code analysis experience across all the other tool chains as well. That's a North Star that our team is looking into. There are a few ways you can connect with us. You can reach out to us using the Visual Studio feedback for feedback and suggestions. You can contribute. We take a lot of suggestions on checks or fixes. Even if you can, contribute to tests or ideas, bug reports, we welcome any kind of contribution. A lot of the checks we work on is heavily guided by the feedback from the community. And you will see that when we blog about these, we acknowledge these community contributions. And that's definitely a big part of the prioritization for us. So do keep that feedback coming. Follow the C++ team blog. This is where we make most of our announcements. And we have a bunch of resources that you can go over. There is first, I left you with a link on the GitHub Actions. if you want to read about code analysis overview for C, C++, there's a link to that. There's a link to ClankTidy. ClankTidy is a great linter that we have integrated both inside of Visual Studio and very recently inside of VS Code. If you want to contribute in Microsoft GSL, I have a link to that as well. If you haven't checked out CPP core guidelines, do check that out. I have a link to that. And if you are curious to write your own GitHub Actions analyzers on GitHub, there is a pointer to the static analysis results interchange format, or SARIF, which is a JSON format that your tools can produce. And that makes it really easy for you to integrate that tool inside of GitHub. That brings me to the end of my talk. Thank you. Right. I see a question from Sai here. Maybe I can take that.
Yeah. So thank you so much for your talk. Yeah, I think one thing which is very useful for me, especially, is the compiler explorer support. I quite often like to make little samples or prototype things on compiler explorer, and having the static analysis support as well as the nether support for execution on MSVC toolchains as well on compiler explorer is super useful for me. So yeah, we have a few questions so far. Feel free to keep questions coming. We're good for time, so we can answer a bunch of questions. So we have, how do you enable the static analysis in Visual Studio?
Sure. Right now, static analysis is enabled by default. As you are working in a C++ project, it runs in the background, and it shows results as green squiggles in your project. So you don't have to take any explicit action to be able to analyze static analysis, to be able to turn on static analysis in Visual. It's just on by default. You just need to pay attention to the green squiggles. As you hover over them, you will find what they are telling you and then take some action on it.
Cool. And which rules will be enabled by default? All of the rules, or are there ways to enable and disable different rules?
Right. So by default, we have this notion of Microsoft native recommended rules, which is a subset of the rules that we ship. It's not all the rules, definitely. We are trying to prioritize rules which are more I would say which tend to find more bugs in real world code. And so you will find a subset, but there are ways for you to go. If you go to your project, and you can go to your code analysis tab inside of your project menu, you can select whatever rules you want to customize for your own project. And one of the things we realize is the notion of default can vary, because somebody who is writing a modern C++ app will have a different notion of default than somebody who is targeting device driver, for example. So one of our priorities is to evolve that story, and instead of having one notion of native recommended rules, we want to slice it up by depending on the C++ target that you are writing your code for. So in the future, stay tuned for improvements in that area.
Yeah, makes sense. And how about if someone's wanting to run static analysis tools from the command line or from other tools? How would they go about that?
Yes, we have a blog. I'm happy to share that link to that blog later on in the chat, but we do have a blog on how you can enable static analysis in other, not just Visual Studio command line, but other build systems. Essentially, we are driven off the compiler. So you have to add a few options to the compiler. And the blog goes into the details of how easy it is to configure that in other build systems. And I would be happy to post a link to that later on in the chat window.
Cool, perfect. Any other questions? Feel free to add them to the public chat on Learn TV, and we'll be able to answer them live. What are you most excited about coming next in static analysis?
I think what really keeps me excited about the next set of features that we are working on, like I said, is the next set of safety checks. So it's great to see, when we get these reports from the security teams, and they send us, hey, these defects have been caught in production software. That's really exciting for us, and I feel like it kind of keeps the motivation going. What also excites me is this possibility of building this consistent tool in experience across toolchain. That's an ambitious project, and there is a lot of unknowns at this point in time. But I see a lot of commitment and passion from not just the analysis team, but also the compiler team and the community at large. In working towards that platform and making C++ an even safer language to use. So I think I would say those are like two exciting areas for the team. And making this part of inner loop, that's also something that we often overlook. Like we keep investing on on the checks, we keep investing on building these platforms, but it's super important to also be able to make these checks discoverable and expand our surface area. So we have we can do more in GitHub. Right now, our experience is only targeting CMake, for example. So maybe we want to do that for MS Build as well, MS Build projects as well. We want this to be like right now we have in-house solutions of integrating this as part of like Azure DevOps. So we want this to be easily integratable to like any build system that you're using, and not just Visual Studio, but also your PR loop. So we want to like blog about like our story on how we, for example, for the US regulatory requirement, we did a lot of effort in putting this in the inner loop for our own developers. And I think there are useful learnings we can share that maybe other teams can benefit from. I mean, it's really easy to integrate this, and we should be also investing there. And that's an exciting thing for the static analysis team, to make it more discoverable and easily integrated into the inner loop.
Yeah, for sure. I'm not seeing any other questions. I got one other of my own, maybe on a slightly different note. You talked about trying to get static analysis, which is cross toolchain. How do you see general compiler errors fitting into something like that? Do you think they would factor into that kind of cross toolchain reporting system, or would this be a different kind of thing?
Yeah, in my mind, I think the line is going to get blurry, because if the abstraction that we are working on takes off, then you can do a lot of semantic analysis in your program, and you can use an abstraction that is far away from the compiler. So the beauty of that is the tool chains might change underneath, but your abstraction is going to be relatively stable. So at that point, the kind of errors that you detect may not be just tied to analysis errors, but you can also, compiler warnings are mostly, implementing some dialect from the standard. You could also do that in that abstraction. So I think the line is going to get blurry, because you may have some errors which are closer down using the tool chain that you're using, but you can definitely have some errors which are implemented in that abstract layer. So that's something that will happen organically, and the line is going to get blurry. Like we'll probably have a more integrated experience, and right now I think analysis is like compartmentalized. Like you have first the batch compilation with all the errors, and then you have another pass where analysis runs with these additional checks, and I think that line is going to get blurry, and it's a good thing.
Yep. All right, great. Well, thank you very, very much for your talk, and we'll see you next time, maybe.
Right.
All right, we're back on track for time, so we're just gonna kick straight into the next session, which is Gabriel Dos Reis, who's gonna be telling us about program representation in C++. Hey, Gabby, how are you doing?
Oh, hello, Sai. I'm good. How about you?
Good, yeah, excited for final session of the day so I can go get some food. I haven't eaten yet. It's like, it's usually my dinner time.
I agree. I also need breakfast.
Yeah, it's like 5:20 my time, but morning for you. So,
okay.
All right, take it away.
Okay. Hello, everybody. I'm Gabriel Dos Reis. I'm architect for Visual C++ at Microsoft, working on C++ compilers and tools for systems programming. Today, I wanted to share some of my thoughts on persistent representation of C++ for fun and profits. What am I actually talking about? I'm talking about the idea of making it easy for all C++ developers to have access to the same representation of C++ programs that their compiler have, and have this being done by the community, and the facilities developed over this developed by the community. And part of why what this project for the community is that when we take C++20, which came with a loaded bunch of new features, one of them is modules. The conventional way that C++ compilers implement modules is that they work to build a very nice, complete, semantically complete representation of your modules interface. They save it on disk, and when you import a module later, they just load that in memory and then merely go by their job. And when they're done, they just throw that away, kind of waste. And the other thing is that if you really want to use C++ to its fullest extent, you really want to have access to the highest levels of abstraction. You do not want something like extern-C something. You want the template, the concept, the Constexpr, function bodies. You want to compose those things, right? So how do I get there? Well, the idea is, well, C++ is a very complicated language. Everybody will tell you that. But it's not impossible. The way you get there is that you aim for something that is general, more regular, general enough to contain all the barnacles of C++ inside. And then you have that semantics, driven and implemented, developed, driven by the community. That's the goal. So the problems with the static query, as I was saying earlier, is that you have these interfaces for C++, which is a language that is really beautiful in the sense that it has zero overhead abstraction. It allows you to have light with elegant abstractions. Then when we build all those things, the next thing we do when we want to talk to another language is we say extern C, which is that we drop right away down to the lowest levels, the ugliest parts, and that's how we communicate with our language. We need to change that. If you have this high-level representation, you can change that, and I'll show you how we can get that done. The other thing is that worries me is that because we do not have a community shared common representation, we have some form of fragmentation. Each compiler vendor would lock in their own solutions, and and it becomes difficult to talk to someone. Like I have code that's working on Windows, want to compile the same thing on Linux or Mac, and communicates between the libraries, for example. And on Windows, for example, I have 3 or 4 compilers, and it's really a shame if we'll have to deal with end format for end compilers, each going by their own way. And this is already a problem for people who are building and shipping modules. And the last thing I want to say is, even though we write C++ programs as sequence of characters, and then we read these things, for automated transformation, that's not really the best representation. We can do better, and that's what I'm trying to rectify. So the central notion about this representation stems from something that C++ compilers have been doing, especially with C++20, which is what we call module interface build artifact. When you compile an module interface, the compiler generates something that contains all the information that it needs to process name lookup, constant evaluation, template instantiation, all that kind of stuff. And then the idea is to reuse that artifact that in many cases will be thrown away. Like it is a notion of waste that we need to get well handled on. We need to be more into green computing with C++. So these artifacts are reused by the compiler, and the compiler knows them. The compiler really takes advantage of your hard labor. Like you work very hard to write your program, organize everything. Compiler look at it and then takes advantage of it. Concretely, here taking an example, the MSVC tool set, but the GCC toolset, client toolsets, quite similar in structure. So imagine that I have the interface file, right? This is IXX, and then I have an implementation file from Azure. It's a CXX file. When I compile that, usually it would generate a compilation step, would generate a bunch of object files, and then I can link them and produce either an executable, or I can get a shared library, either .so, .dilib, or DLL. But at the same time that those interface files are being compiled, the compiler also produces this metadata with the MSVC compiler. It is .ifc file. GCC will be what they call CMI, which is compiled module interface. And if you Clang, it is PCM file. But essentially, it contains a high level, a very structured representation of your module interface. It's a module interface of header units and of those structured PCHs. Now, the nice thing about the IFC file, the BMI, whatever you want to call it, is that they offer the exact same semantic content as the original input source file. That's just a sequence of characters. However, if you understand how that structured data is saved on disk, you no longer need a C++ compiler to actually process it. So you don't need to know anything about the lookup. You don't need to know anything about the resolution or that kind of stuff. You can just write your Python script or TypeScript scripts or whatever scripting language you use, and just go and merely plot through that file and get the same and enjoy the same benefits as your compiler does when it processes your C++ file. And by doing that, now you see that we kind of like democratizing, giving the masses, everybody, the same access to those data, that high-level semantic representation as the compiler. And the interesting thing is that once you're able to process this metadata file, you can generate anything that you want. You can generate introspection, like at build time. You can generate new source files out of it, or you can even save that file at the runtime, have your program open that file, and then act upon its content, right? If you want to provide a type-safe linking or computation, like marshalling data and send it over network to a different machine, and that different machine understand how things was byte, for example, they are doubles or they are long integers that are part of a structure, and unique pointer, that kind of stuff. Just being able to get the actual representation, how it is done, and the description of it allows you to automatically generate code that bridge the gap. This is really a enabling technology for the C++ community, and it would be a shame to let it go to waste. So, in short, while your compiler is benefiting from your hard labor, you too can benefit from C labor, right? So, like you said earlier, you know when you compile, you produce these IFC files. You can use those IFC files if you understand the structure. You can generate new C++ files that are compiled and linked into your program, or you can generate resource files that are compiled to do something else, or you can just generate some monitoring program so you can do some kind of introspection. This is new. This is powerful. Okay, but to get there, you really need to make sure your C++ tool vendor is not hiding the structural information of these metadata from you. If they are, please tell them they shouldn't. They should stop. They should tell you what they look like. Okay, so to get there, to get that structure of the binary representation, and for it to scale, to the places where C++ is used, you need a complete representation. You need something that's very efficient to process, and to avoid vendor lock-ins, or at least to minimize it, you want a representation that is compiler neutral. So it's very ambitious, and people will tell you it is impossible. Well, it's easier to say something impossible than to actually get in and make it happen. And I want us not to take the easiest part, but actually make it happen, because the reward is greater than just denying and basking in laziness. So to have this representation, when say compiler neutral, people say, well, do you mean that we have to take the union of all the compilers on the planet and then put all that things in a big spec? That will be unmanageable, and that will be true. But that is not the only way to go about it, right? Like I said, we can find a more general representation framework in which we can express all of these variants, and that is possible. And that's what I want to talk about. To get there, it requires engineering and science, right? So I'm talking about the engineering choices that I made during this project. The first thing is to abstract away from concrete syntax. So what I mean by concrete syntax is all these grammar productions that go around. But what you want is you want a mapping from the concrete syntax to the semantics resolution, and make sure that the semantics capture absolutely everything. And then you have a way to go from that mapping is you can reverse back to the concrete syntax. And again, you have to focus on the semantics, really the semantics, not the syntax. C++ has too many ways, for example, of initializing variables. Most of them differ very little by syntax. What you want is to capture the semantics so you can reduce the complexity. The ISO standards has drawn a lot of barnacles, right? And there's a bunch of irregularities. You do not want a representation that faithfully mimic those structures irregularities. You want something general in which you can express restrictions enough that reflect those irregularities, but you don't want a representation that itself is so ugly, is so tortuous. Okay, and then in that framework, you need to have a way to represent vendor extensions, because, well, let's face it, in real world code, you all have extensions, and that's the way things are. When you look at, I was saying earlier, don't focus on syntax. When you look at the ISO grammar, this is count that I made, a couple of weeks ago. Well, I have about 348 production, non-terminal production, and I'm not counting the size of each production. I'm just counting the non-terminals. Right? Okay, it's about 350. And it kept changing. When the structure of them keep, every time that the C++ committee meets, there is a high risk that these rules or grammars will change in form or in some sense. Okay, so we cannot use that as the basis for this simpler representation. We have to move to something else, which is the simplicity, the generality, the regularity, and remember that when we talk about semantics, the best way that we know in computing to represent semantics is to rely heavily on types, because types are the best approximation that we have for runtime semantics. And we know we can make it minimal. It is very important that we have this representation as minimal as possible for people to be able to navigate, to deal with them in practice. And like I said earlier, compiler neutrality is really important, because we want these representations across our platform, all compilers. And of course, we want to be able to scale this. Like, I'm traveling and then have only my laptop. I should be able to handle hundreds of thousands of lines of code on my laptop during a long flight. So, must be very efficient. To get this on disk, persistent on disk representation, I took a lot of inspiration from a work that I did with Janus Trostrup about 15 years ago or more, and it was called the IPR, which internal program representation, very imaginative naming. So the idea with the IPR is that we have class hierarchies, we have templates to capture commonalities, and then we have interface that separates. Like when I say interface, I mean pure virtual functions, abstract classes that so that I can separate the real interface and the ugly implementations. And the ugly implementations can evolve, but if the users, consumers, only take dependency on interface that are relatively stable, you can have wider adoption, can apply the framework to much wider scenarios and over a longer period of time. Now, when you're writing something on disk, you don't have vtable. Like class hierarchy is just essentially means vtable, and then you overwrite stuff. But you don't have that when you're writing on disk. All you have access to is some kind of switch statement, tag, or whatever it is. But if you take a step back from that low-level view of representation, like what is it really we're trying to do, you realize that, well, we are trying to describe data structures in a principled way, and the go-to field for that is universal algebra or multi-sorted algebra to surface commonalities. And then you're going to have a bunch of types, things, but most of them will share some structure commonalities, and then you apply the principle, the generic programming principle by Alex Stepanov called gradual lifting. Just you start from something very concrete, very concrete situations, and try to literally, gradually try to find commonalities, and so they can have something more generic that when you instance it back, you get exactly the same scenarios that you started with. And, this is engineering, so you'll have to exercise some taste and common sense. So when, doing that concretely with the MSVC toolset means that I started with the Microsoft compiler. It could have been GCC, it could have been Clang, but in the last 8 years, I've been mostly working on the MSVC compiler. That's the thing that I had. And then start abstracting over details. Remember, I want compiler neutrality. So you need to abstract over implementation details, over specific compiler ugliness. And slowly abstract over and make sure that you can instantiate these things with other compilers. And you get something that's quite useful, beautiful. So those 3 steps, I think, are the essential keys to this project. I've already done part 1 and a bit of part 2 and some of part 3, but I really need a lot of help to complete step 2 and 3. It's a process, but I need your help to complete step 2 and 3. And if you're interested in how does this C++ algebra look like? Well, they are very much analogous to C++ concept, which is another big feature in C++ 20. But essentially, you take a step back and look at how things are structured. For example, if you take a declaration is a specification of a type for a name in a scope with some initializers, right? When you look at it, you say, well, what is a type? Well, a type is, has basic type, and I can compose new type of basic type like pointers. I can say star int, and that becomes pointer to int. But then if I say array to the array of int and 5, then I say that I have a type int and I have an expression 5. So a type is the algebra. It's combined of the algebra of type and expression. And statement, you can have declarations, and you have expressions, types, and directives and attributes. So you see that when you start with this the hierarchy: type, declaration, type, names, expressions, and directives and attributes, then you have some kind of cycle in there. But it's really important to tease those cycles out and have a sense of how they relate to each other, right? So if you, for example, if you're trying to parse a declaration, you need to know how to parse a declaration, but then you also need to know how to parse a type, an expression, a statement, which can itself contain a declaration and so forth. So that gives you a high-level view of the structure that you need. So the product of that, the outcome of that project, which is to have a a uniform, simple specification of data structures capable of representing all of C++, not pure enough to present all of ISO C++, is what I call IFC. IFC is the format that the MSVC toolset uses to represent modules interface in binary form. So this project is open to the community. It's on GitHub. You can check the link there. You can use it. It has a very permissive license. You can use it as you see fit. The only thing you need to say is give credit. And of course, when you use it, you're very happy with it. Please contribute so that the rest of the community can benefit from your work, and together, when we contribute, the project grows bigger, and the rewards, the outcome is not just the sum of each individual, but it's much bigger. Okay, so in short, an IFC file is just some kind of binary format today used by the MSVC toolset to represent metadata. And when you compile a module interface, or you want to turn a header file into what we call header unit, which is that you just pretend that that header file forms a self-contained entity in its own, and you want to have the representation, the semantics of that, you save that in binary format. And the structure of it, as I said earlier, is based on the IPR project, which is something, it's a project I worked on with Bjarne. It is exceedingly simple to process. Like, you do not need a C++ compiler. Once you get your hands on the IFC file, you do not need a C++ compiler to process it. You can just write a very dumb script in Ruby, Python, or any other scripting language that of your choice. Of course, you can also write a program in C++, but it is not required. Or you can even, write it in JavaScript and view in a browser. And it's wonderful. So what do you find in an IFC file? Well, you have declarations, you have types, you have statements, expression names, everything that you see in C++, right? And then when you double click on those general categories, you see that, well, you also need to be able to represent strings. It's lower level source locations, because you need this kind of mapping between input source file and the semantics representation. You need token streams, because guess what? You have attributes, you have a bunch of other stuff that are just token streams. And you need to represent macros, especially to handle header units, and I call them preprocessing forms. And then you have a bunch of other, stuff that called heaps, just a blob of stuff. And you have some look-aside tables to deal with specific compiler extensions. Like, if I'm dealing with GCC, how should I interpret certain sequence of abstract references? The same goes for MSVC and so forth. Sometimes you need to save the internal states of the compiler so that you can resume it later, especially when you're dealing with something you need to do when you're dealing with anything with the preprocessor, right? Macro expansions and warnings, that kind of stuff. Now, the end goal is that we have all of ISO C++ and beyond, because we need to be able to represent extensions. The way we deal with this, to have simplicity, is that it's very hard to beat tables. So we start with homogeneous tables, arrays, and we call them partitions. So we have a bunch of data in homogeneous arrays, and then we refer to those the entries of the partitions by abstract references. And every abstract reference is the 32-bit value. And there is a portion that's a tag, and there's a portion that's an index into a partition. So when you get an abstract reference, if you know the tag and you know the index, you're good to go and fetch the entity that you're referring to. So concretely, an IFC file, this is how it looks like. You have the 4 bytes, that just sequence of byte, signature that tells you that this is an IFC file. You're supposed to interpret this file, binary file, as an IFC file. And then you have a certain number of bytes that are called a header that describes how to find various information in there. It has, for example, pointer to the table of contents that describes where to find specific things, and then that's followed by partitions. Remember, partitions are just homogeneous sequences of entities, all of the same type. And like I said, a partition is just a homogeneous table. It has a name, so you can say, oh, this is the declaration of classes, or this is variable declaration, or this is a function declaration. So it's a name. We have string you can use to refer to partitions, and you have a 4-byte integer that tell you where to find that partition from certain positions from the beginning of the file, and how many elements entries there are in that partition, and each partition, what's the size of essentially how many bytes each entity in each entry in that partition occupies. And of course, like I said earlier, an abstract reference is essentially 32-bit value. We have a tag and then have an index. The tag is the thing that allows you to look up the partition that you need to look at, and the slot is given by the index. And it is quite simple. You can think of this abstract reference as some kind of strongly typed pointers. This is not voice star. This is a different kind of pointers and well structured and typed. So remember, when you take an IFC file, the 4-byte just tells you this is an IFC file, and then you need to look at the header of the file, to get a sense of how to interpret the file. So you have a checksum, which is just some kind of hash of the content that you can look at to make sure that the file is not obviously tampered with. Here, say obviously, this is just a quick check. It is not a thorough, complete, safe check. But most of the time, if the check is, it's quick. If the checksum doesn't match, something wrong happened. So you have the versions of the IFC format. This is something that we evolving with the community. So we'll have several versions of the IFC. You have an indication of the ABI for which this IFC file has been produced, and which architecture, and also which version of the language. Is it C++ 11, 14, 17, 20, 23, or 2025? We don't know. And then the next thing that's very important is the string table. Remember, each partition is named. The way you look them up is through their name, right? So you quickly need to know where to find the names, and all the names, strings, everything is something called the string table, just a huge array of characters, all the characters that appear in the source code in some form. And then you have a description of the translation unit. Is it a primary interface? Is it a partition interface? Is it an internal interface? Is it a header unit? And also the path to the source file that was used to create the IFC file. And then, start the fun, which is that you have an index into the first declaration at in the global scope. Everything starts from global. All declarations are written in the global scope. So get an index into the scope, and then from there you can start fetching all the declarations that you're interested in. Of course, you want to know where is the table of content. Table of content describes the partitions and where they are and so forth. So because C++ is complex, it's clear that you have a bunch of entities. You have declarations, and also that gives you a declar index type. You have types, expressions, names, charts. So those are parameter list. You have strings, and then you have preprocessor forms, and then in scope, and then you have string literals, right? And then you have tokens, and then sequence of tokens. Sequence of tokens are just sentences, right? That's how things were. So once you've known these things are possible. So this is not science fiction. This has been shipping in at least in MSVC compiler for a while now, and the spec, you can find the spec on GitHub, link I provided earlier. So once you have these informations, what is next? Well, what I really like to see is that the entire C++ community rally to collaborate for the C++ community to define this representation. Okay, if someone comes tomorrow with a much better representation of the IFC, I'll be first to jump on it. Like, I'm not particularly attached to this one. What I'm attached to is the idea that we have a common representation, not common representation to Windows developers only, but common representation to the entire C++ community. It's together that we thrive, okay? And, so we have to start from somewhere. That's why I'm putting the IFC project forward. And the development is in the open, open an issue, start a conversation, and let's have that. And there are libraries out there like the IPO that are trying to create data structures, in-memory data structure from the on-disk representation. And in the previous talk by Sonny, you heard him talking about desire of having uniform experience of static analysis across all platforms. So if we can have something like the IFC, then and your compiler GCC is able to produce an IFC, and then you can just load it in a Clang tidy, and then run your Clang tidy analysis. Or conversely, or it could be an MSVC. Not all these three compilers have the same analysis, but if you have a shared notation, just like we have a shared notation for C++ program, a sequence of characters, if we can have a shared notation of a much better representation, we can share a lot as a community around regarding the tool set. So I say a final call to action. What I would like to do is please go to GitHub, github.com, Microsoft IFC spec.kit. Clone it, build it, look at it, find all the bugs, find all the things that are wrong with it, file issues, start conversations, so we can make it better. Okay, and if you want to play with it, you can also clone the IPR library, and you can start building IFC data structures out of the IFC. You can use today the MSVC toolset to produce IFC, and then you can write your own library or start a project to get an IPR library, parser that builds IPR data structures from the IFC. Or they could be your own data structure. That is also fine. But let's do this thing together. Let's have fun together. Okay. And of course, I need your help for this thing to actually succeed. I need you to go and talk to your C++ developer tools providers so they do something about the IFC, or just something similar to the IFC, but something common, so that we can all share the wisdoms that we develop through programming in C++. With that said, I'm ready to take questions.
Thanks so much. Yeah, I definitely echo that call for people to get involved, and that this needs to be something which happens across the community and across vendors, and so that we can all benefit from it the best we can. So we've got about 5 minutes left. We're pretty much straight on time. So we've got time for questions. If anyone would like to ask questions to Gabby, or I don't know if we have all the other speakers, but if anyone has any questions about any of the other talks as well, we can either get them up, or we can forward the questions onto them for them to answer offline on Twitter or something like that.
So are the questions on Elon TV or on StreamYard?
There will be. I have the technology. I'll let you know if there are any questions. I don't see any right now.
Everybody is ready for lunch, dinner, or something.
Yeah, that's good. I do have Marshmallow has woken up and is was on my lap earlier watching all of the talks very, very intently. All right, not seeing any questions, so I think at that I'll say thanks very much, Gabby, for your talk.
Thank you.
Okay, and with that, we're going to close out. Thank you very much to everyone who joined in from whatever platform. Very much appreciated. I hope you all enjoyed the conference. If you would like to watch the sessions, they will be available on demand, both on Learn TV later and I believe on YouTube. So you can check those out later if you'd like to reference anything or send them to your friends, things like that. We also still have a bunch of pre-conference sessions, which are also on Learn TV and YouTube, which you can check out. We have, I believe, 10 talks on everywhere from MSVC update for C++20 and C++23. You can check out aka.ms/purevirtualcpp/on-demand to find all of that content. And I hope to run this again next year, so I hope we'll see you all there, and thank you very much.